the InfoH Space Exploration Center live Zoom event. It goes from 10 a.m. to 4 p.m. It's the longest Zoom that I have ever attended, and I hope that you will feel free to come and go as you please. It is the 75th anniversary of Project Diana, and at 11:58 this morning, at the exact same time that the original moon bounce was done, we expect to bounce a signal off the moon. And with that signal, you can send your voice to the moon and back and travel 500,000 miles. The schedule is as follows. At 10 a.m., I am giving this introduction. 10:30, Dr. Daniel Marlow of Princeton University will speak about the TLM-18, which is the antenna that we have on site today. That antenna gives us the ability to look at pulsars, other galaxies, interstellar space. We can monitor weather satellites and download information that allows us to generate an image that tells us where hurricanes are. Then Ray Chase and Al Klase at 11 o'clock will reveal new information about Edwin Armstrong's contribution to the success of Project Diana. At 11:58, that's when we intend to do the first live moon bounce over Zoom. And I'd like to be able to bounce everyone's voice. If we have many, many participants, we have a second Zoom meeting that you may be able to go to in order to bounce your voice individually. At that time, when I do the moon bounce at 11:58, I will ask everyone to send their voice to the moon at the same time so that you know that you've done it. At 12:15, Cindy Stodula Pomerleau, who is the daughter of E. King Stodula and is debuting her new book today, which is available on Amazon, will speak. The book is To the Moon and Back, The Life and Times of Project Diana. I am so looking forward to hearing her speech because these guys were regular men and women who came to work every day, had regular lives at home with families that needed to be attended to, and I think that that's a really important thing. They did great groundbreaking work and had normal lives at the same time, just like us. At 1 o'clock, Fred Carl will speak about space exploration after the moon bounce. After all, the moon bounce was the beginning of space exploration. And he'll talk about the big year. At 2 o'clock, Charles Cebula will speak about Dr. Walter S. McAfee, a hidden figure and pioneer of radar. Without his mathematics, it would not have been possible to calculate for any point on the moon from any point on the Earth, and thereby compensate for the Doppler shift. Diane Mercedes McAfee, the daughter of Walter McAfee, will speak afterwards, and they'll take your questions after 2:30. At 3 p.m., we'll see a video that Frank O'Brien has prepared for us. It's called Radio in Space Communication, because the radio that we used in 1946 for the moon bounce is used today and will continue to be used in space exploration throughout time. So let's begin. This is the Zoom meeting information for the second meeting. Please write down or take a screenshot of this so that you have the meeting ID in case you want to bounce your voice individually through another Zoom meeting if we have too many people at 11:58. And let's start. InfoAge is a nonprofit organization, and our mission is to preserve science and history. So please donate. This is a free event, and the moon bounce is a free event through the FCC. But let me tell you, we need help. So please consider donating to InfoAge. There's a great link at the bottom of this page. Use it if you possibly can. Thank you. Project Diana. Bouncing a radio signal off the moon was the first attempted by John DeWitt in 1936. From what I understand, he did not succeed because of several things. There was a pulse transmitter that they dubbed the ice cream freezer. The experiment failed because they did not have sufficient transmitter power. Here's a photograph of these guys trying to make this happen. And it kind of does look like an ice cream maker, doesn't it? However, in late 1945, following the end of World War II, scientists at Camp Evans began to work on a way to prove that we could pierce the ionosphere, not only from the Earth, but also from above the Earth. And that was the important thing. Imagine a human race never having heard a radio signal transmitted from above the atmosphere. Could we possibly be that isolated? Was there nothing out there that could send a radio signal? This is something that had to be answered. Mathematically, we knew that it was possible. We thought that it was possible. But unless it's done, it doesn't happen. Project Diana, named for the Roman goddess, was initiated using radar equipment developed during World War II. Here are the men of the 1946 Project Diana team. There were Lieutenant Colonel John H. DeWitt, he was the project leader, E. King Stodela, Dr. Harold D. Webb, Herbert P. Kaufman, and Jack Moffinson. We're lucky enough to have been in touch with all of the family members of these men, and they have wonderful stories to tell us about the lives of these people. Here they are. This is what the Diana site looked like in 1946. You can see that there are all sorts of things. There is the SCR 271, maybe the 272 in this picture, and there's a smaller antenna. There are small radar trucks. And this site was basically used specifically for radar research. It was the Army Signal Corps area. The roads were barely made at that time. And if this picture were a little bit bigger, you could see that across the way along the Shark River, there were no buildings. There was nothing here. This is where the first moon bounce was done. Here we have the SCR 271 and the story. Look at the truck. I'll tell you that it's 1946. So the SCR 271 was not sufficient to complete the moon bounce. Imagine going to work every day and trying to do something like this and failing day after day. You make your lunch in the morning, you get in your car, you drive over, you try again. It didn't always work. It didn't work at all until January 10th, 1946 at 11:58 in the morning. We'll learn today about what the things that did happen that were making the moon bounce possible and how everything that was learned along the way made it happen. This is the kind of equipment that was being used at that time. And there it is. The SCR 271 had an extended bed spring, and they thought that that would help, and it did. And due to the precise frequency control that was required, we needed a special transmitter and receiver. And it was Major Edwin Armstrong who was able to create that kind of transmitter. I understand that his transmitter is still being used in some ways. Transmitted power was 50 kilowatts at 111.5 megahertz in 1/4 second pulses. Look at the equipment that was used then. Dials, handles, wires everywhere. Today, the flick of a button or two, we do the moon bounce. This is Colonel John DeWitt. There's a newsreel that's available on YouTube of John speaking about the success of the moon bounce. And he says something like, Before now, we didn't know whether we could communicate with anything above the ionosphere. Now we may be able to build spaceships. When I watch that clip, I think about people who say that things are impossible to do. And until the moon bounce was done, it was impossible to think about building a spaceship. What is it today that we think is impossible? But if we have the technology, will definitely be possible in the future. This is what the return looked like. You can see the original signal being sent, and then you can see that the signal has gone 238,000 miles and returns back. It was called the Echo. We learned that the moon's diameter was 2,159 miles at a speed of light of 186,000 miles per second. The ionosphere covers the Earth 38 miles up, and the thickness of the ionosphere is 250 miles. There was a comic strip that was created by Harold Webb about the moon bounce. And if we went ahead and read each of these pieces, it would be very difficult to watch our time. However, this comic strip was published and is very, very interesting. People laugh at us now, he says. One of the team members, Dr. Harold Webb, became the father of a daughter in January 1946 and promptly named her Diana. I have a statement that I'll read about what Diana wants to say. She's not able to join us today, but she did give us a statement. Dr. Webb also created a comic strip depicting Project Diana experiment and went on to predict interplanetary space travel, missile development that eventually came to pass. These people were visionaries. They saw things that others didn't, and they weren't afraid to try, and they weren't afraid to fail along the way in order to achieve the great thing that they did. Dr. Webb went on to an illustrious career in radio astronomy. Dr. Walter McAfee was a civilian astrophysicist, and his mathematical calculations were vital to determining the expected Doppler shift. He also calculated the reflectivity coefficient of the spherical moon to establish other technical parameters. Without Dr. McAfee's help, the moon bounce wouldn't have been possible. And here is a picture of Dr. McAfee as this, I guess, plaque or road sign was dedicated to Project Diana. The birth of radio astronomy, the beginning of the space programs, Earth-Moon Earth transmission that ham radio operators around the world love to do if they have a big enough antenna and radio. The ability to send a signal from one part of the Earth to another part of the Earth using the moon. The ability to explore space. And this project, of course, was the beginning of the tradition of naming space programs after ancient Greek and Roman gods. You can think of Mercury, Gemini, Apollo. This is the QSL card for the moon bounce. And I think that ham radio operators understand what this means. It is a confirmation that it was done, and it was done here at Fort Monmouth, New Jersey. And if you're not sure whether this is true, here it is. Contact with the Moon, made by radar, New York. It was pictured at the Institute of Radio Engineers Convention at the Astor Hotel on January 24th, where, there they are, the names of the people who were involved. Colonel John D. DeWitt, head of Project Diana. Scientific history was made on January 10th of that year at this laboratory, and it was the birth of frequency energy shot directly to the rising moon, and it was returned 2.5 seconds later. And we cannot change that because today it takes 2.5 seconds for the signal to be sent and heard back. Thank you for viewing. If there are any questions, this is a great time to ask. So please unmute yourself at this point.
Unmute.
Did the signal increase the accuracy of determining the distance from Earth to Moon?
It does, yes, it did, of course. But we understood that we knew the distance between the Earth and the Moon by this time. But of course, being able to send the signal gave us much more information, so we could specifically say 238,000 miles. Today we say 250,000 miles, but approximately 238,000 miles is closer to the exact distance between the Earth and the Moon. Any other questions? Yes, Ovid. Ovid.
Also known as K8EV. Just a comment on the QSL card. I believe that is a subsequent a card that was sent out subsequent to the original moonbows. If you look at the power level, I think it's 19 million watts, which would have been great at the first moonbows, but I don't think that was the power level. And it was subsequent and was clearly not secret. I think what they were working out was the ability to communicate with satellites. Take a look at the fine print on the QSL card. I think you'll see a little more information about it. That's all I wanted to say. Thank you.
You're welcome. Obviously, what happened was that as soon as the moon bounce was done and we understood what it took to do it, the transmission power, the kind of antenna that we needed, ham radio operators were very excited and they attempted to do the moon bounce. In fact, here at ISEC, we have the equipment that was used by the second ham radio moon bounce success. So Ovid, I think you're right. Any other questions? Okay, let's take a little bit of a break and then we will come back. Let's see, it's 10:19. We can come back at...
Or Lori, don't you think we should just keep going or?
Well, we could just keep going if you'd like. Dan, you have, you're scheduled for 10:15. Would you like to speak now or do you want to wait until later?
I'm ready to start now.
Okay.
Yeah. Okay, so let me just
introduce Dan Marlow. Dr. Dan Marlow, who is a physicist, a specialist in the muon solenoid, and I really don't know much about it except that it's a particle, and he knows all about it. Dan has been the chair of physics at Princeton University, and he is graciously our technical director here. He has written the radio that allows us to explore the universe, and he's always updating, and he's always very helpful in making sure that everything works. So Dan is the expert about how the TLM-18 Space Sentry radio dish antenna was refurbished in the early, I guess it was 2006 that the restoration began. The dish that we have here was placed in 1958, and it was used until sometime in the mid-90s, and then it was abandoned by the Army Signal Corps as they left this area, and Fort Monmouth was located primarily at in Eatontown, New Jersey. And I think it took a lot to get this dish up and running. I can remember a time when the first thing they had to do was beat the rust off of it because it literally sat there and rusted solid. So Dan, can you tell us what that experience was like?
Will do, Lori. First thing, I'm going to do a little housekeeping here, and I'm going to make you the host so that because people continue to arrive.
I see them, yeah.
And so you can take care of that. All right, so you should be the host. And now I need to share my screen. And let's just see if that's possible.
And I'm going to go ahead and stop sharing.
Okay, so are my slides up?
Your slides are up.
Okay, very good. So thank you, everybody. Thank you, Lori. My name is Dan Marlow. And as Lori said, my day job is to teach physics at Princeton University. But as a sideline, I help the InfoAge Space Exploration Center. And in particular, with the original job was to restore the TLM-18 to operation. So let me see if I can advance my slides. Okay, so here's what I'm going to talk about today. I'll talk about the telescope itself, some of its history, and then go through its various capabilities and just say a little bit about each one. Missing from the list is EME, although I think I have a slide in there showing how that, showing some things about that. Okay, so this is a reasonably recent photograph of the dish. You can see obviously the dish itself. It's a 60-foot or 18-meter diameter dish. I'll talk a little bit about what we have at the focus of the dish. To the right of the dish, you can see the control room. This is the same building that was used for the Diana project. And it now, and subsequently served as the control room for the dish and is still the control room for the dish. It's also a small museum and it's open. Well, right now we're not open because of the pandemic, but under normal times, it's open at least 2 afternoons a week, Wednesday and Saturday, and also Sunday, Lori?
Yes, we're open on Wednesdays 1 to 5, Saturdays 1 to 5, and Sundays 1 to 5, unless we have a special event like this.
Yeah, okay. So anyway, all right, so a little bit of the history of the dish. This dish is a Cold War relic. It's located in Belmar, New Jersey, or near Belmar, New Jersey. So that's just a few miles from the New Jersey shore. It's the former site of Camp Evans, which was part of Fort Monmouth, a U.S. Army R&D site. As Lori talked about, this site was used for the first moon bounce experiment in 1946. That was a different antenna, which is long gone. In 1960, the TLM-18, this dish, received the first weather satellite images from space, and the satellite was the Tyros. Some of you may have some experience with the NOAA satellites, the polar orbiting satellites, and Tyros was a forerunner of those. So the TLM-18 was also used in classified research until 1980 or so. After that, it sat fallow for many years, and then a small group of us refurbished the dish in, it took us roughly 3 years from 2012 to 2015. Okay, so this is the Tyros, and I won't read that. I think pretty much everybody now knows the importance of these weather satellites, especially when it comes to hurricane prediction. The saving of lives and property is enormous because of our ability to see the hurricanes coming. Okay, so this is a photograph from 1960 when the Army craned the 60-foot TLM dish into place at the Diana site. That's the same dish that was in the photograph I showed you earlier. At the time, there were actually 2 dishes on site. The second dish is long gone. I always liked this photograph. This is when Tyros was passing overhead, And the thing that's unusual would be unheard of today is this character sitting there smoking a cigarette. And that, of course, is we're now a smoke-free facility. Okay, and again, this was a big deal. The image was immediately transported to the White House, and here's President Eisenhower in the late days of administration admiring the image that was captured. Okay, so I'll talk a little bit now about the work we did to get the dish back into working order. Before I launch into that, let me just acknowledge just some of the many people who contributed to this. Fred Carl, who was then the director of InfoAge and is with us here today, was really instrumental in getting this going. I learned about it through a colleague, Norm Jurasik, whose role I'll describe in a minute. And I won't go into the whole story, but I was interested in getting access for our Princeton undergraduates to a more capable antenna for radio astronomy. I learned about it. And at the time, I Googled InfoAge, and up popped Fred's phone number. He had his cell number on the web. So I called him, he answered, and I said what I had in mind. And he said, well, sure, come on down. So my wife and I drove down to the site and had a nice meeting with Fred, and we got started. Okay, so other people, Martin Flynn, W2RWJ, who was a member of a radio club called OMARC and also InfoAge. Martin did a lot to get things going, IT and many things like that. Jeff Gettelfinger is an engineer from Princeton. He did a lot of the mechanical engineering involved in the refurbishment project. Norm Jurasik is a research scientist at Princeton. He works in cosmic microwave background. He was the linchpin of the very famous WMAP cosmology program. And Norm just basically knows everything. And really, in terms of the dish controls and the RF stuff, Norm really led the charge on that, and it would not have been possible without him. Since then, the dish has been handed over to InfoAge for operations, and this is where Lori, today's Master of Ceremonies, comes in. She is the leader of a team of docents. So if you come to visit the dish, Lori or one of her colleagues who I've listed here will give you the tour. Okay. All right. Dish repair. All right. Actually, there's a question, what does TLM stand for? It does stand for telemetry. Okay, TLM 18, it's telemetry 18-meter dish. I should mention, since this has come up, there are many of these dishes around the world, many of them still operating. A series of them were built. They're perhaps most famously deployed starting at Cape Canaveral and then on down through the Caribbean and into the South Atlantic. And they were used to capture telemetry from the early rockets as NASA and its forerunners, the military, developed mainly ICBMs, but also the rockets that are used in the current space programs or the earlier space programs. Okay. All right, so when we got to this thing, it was actually in pretty good shape. You know, this was done by the military and it was built pretty well. In particular, we got a big old, I think 50-volt DC power supply and hooked it up to the motor that drives the azimuth. And lo and behold, the thing turned. And that was very fortunate, because if that part had not worked, I think we just wouldn't have been able to proceed. It would have just been too hard. There's a 10 horsepower electric motor that sits up at the top of the pedestal inside, and it just would have been too hard to get that out, I think. We were less fortunate on the elevation. So there's a motor that drives a ball screw that pushes on the arm that allows us to change the elevation of the dish. And the motor itself was okay, but the ball screw mechanism was very badly rusted. It had a rust cover that fell off. It weathered and fell off over the years. So that was a rusted hulk. What you see here is us recovering that motor, the whole drive assembly, which consists of the motor and the ball screw, and lowering it to the ground. It literally weighs a ton. The dish prevented us from getting a crane in there, assuming we could afford a crane. So what we did instead is Jeff Gettelfinger designed a small crane, hand crane that was, excuse me, that was hoisted to the top of the dish piece by piece, assembled in place. And then that crane was used to lower this motor drive assembly. And you can see we had a line, we pulled on it with a truck to keep it away from the pedestal, and then it was just lowered down. So that was sent out for refurbishment. That itself was an adventure. We found a company on the web that looked like they could do this work. And in fact, from its web page, it looked like it was this massive national operation. You know, they had facilities in Trenton and Chicago, North Carolina, Houston, all over the place. Turns out it was just a guy with a cell phone who did know a little bit about it, but he was one step ahead of his creditors. And we sent him this thing along with, I don't know, $10,000 or something. And he made some progress, asked for more money. So we thought, well, what do we do? So we gave him more money, and then silence. So somehow our purchasing department was able to track the guy down. He had run out of money. He had basically disappeared, but somehow they managed to find the motor, which had been mostly fixed, or the motor itself, but the ball screw, which had been mostly refurbished, but not completely. And it was sitting in a warehouse, I think in Houston someplace, and this guy owed the warehouse people money. So we had to pay his bill, and then finally we got it out of Hawk and brought it back. And it was far enough along that our shop at Princeton could finish the job. So then we had to repeat the process and hoist it back up. Okay. And at that point, we still didn't know it would work, because there was no way of knowing whether the bearing that supported the elevation was in good shape. But was a very exciting day when we turned the motor on, and lo and behold, the thing moved. Okay, so a little bit about the readout. There are actually two such chains, one for each polarization. And what we have in the feed horn is relatively simple. It's a broadband low noise amplifier, some band pass filters, so that we do a lot of work at 21 centimeters. So we have a fixed filter there. And we also have a YIG filter that can be tuned from 1 gigahertz to 2 gigahertz. And then after that, there's another amplifier to boost the signals up further. There's about a 150-foot run of coax down to the control room. And there we have a digital receiver. It's, if you're familiar with these things, it's an Edis B210. And that basically digitizes the signals and feeds them into a computer. We have a Linux box running GNU Radio. Before I get to that, let's back up and talk about the front end. So here, this horn, at the focus is another horn antenna. This is from an old experiment at Princeton, which was designed to look at the cosmic microwave background at 21 centimeters, or to look at the 21 centimeter radiation. And it's actually a pretty nice antenna. You can't see it, but inside here, it's all corrugated and everything. So it has a very nice pattern. That gets fed up to the amplifier chain that I showed you. You can see the 21 centimeter filters, the YIG filters are in there, and then there are various things that Norm designed in. Okay, all right, and then in at the other end of things, we use this EDIS software-defined radio receiver, and we mostly use GNU radio, and we combine that, or we run that on a Linux machine, and we pointed the dish skyward, or it was actually just pointing straight up, turned it on, and there it is, the 21 centimeter signal. So that doesn't look like much, but we were very excited to see it since it showed that we were working. So basically you just see a big lump of noise and then this relatively small 21 centimeter signal from the galaxy riding on top of it. Okay, so now let me just show you some of the dish's capabilities. One of the simplest measurements one can do is a drift scan over the sun. So basically we point the dish south, and if we pointed due south and at the angle corresponding to the expected elevation of the sun at noon, then as the sun drifts through the beam of the telescope, or of course what's really going on is the Earth is turning, so as the beam of the telescope drifts across the sun, you trace out the response of the dish. The vertical scale here is calibrated in Kelvin, that's antenna temperature. You might think this should go to more like 6,000, but the sun is actually hotter at 21 centimeters than a strict blackbody radiation curve would imply. So we typically measure more like 10 or 12,000 Kelvin. What's most important is the shape of the curve. So you see we get a pretty clean response. There's some side lobes, but they're not too bad. Here we plot the same data, and now we've converted the time to degrees. So you can see that the width, we fit this to an Airy function, and the width of that Airy function is about 1 degree, 1.02 degrees, the fitted width. The expected width from Airy theory and an 18-meter dish at 21 centimeters is more like 0.9, but we don't use the full dish. We under illuminate the dish, so it kind of it's roughly consistent with what one would expect for a dish of this size operating at 21 centimeters. Okay, so why 21 centimeters? Well, it turns out that the hydrogen atom, which as you know, consists of an electron and a proton, has something called hyperfine splitting. And hyperfine splitting comes about because you can the proton and the electron are each tiny magnets. And if you've ever played with bar magnets on a table, you know if you push them together, you can't really push them together such that they're aligned north to north, south to south. They want to flip over to lower their energy state. Well, the same thing is true in the hydrogen atom. The electron magnetic moment and the proton magnetic moment, from an energetic point of view, prefer to be anti-aligned. However, hydrogen atoms can be found in either state. If you bang them hard enough, you can excite them. So they may find themselves in an aligned state, but sooner or later, they'll want to flip over into this anti-aligned state, the lower energy state. When they flip from the high energy state to the low energy state, a photon, which is a quantum of light, is emitted, and the wavelength of that photon, the wavelength of that radiation, is 21 centimeters. So this 21 centimeter radiation permeates the galaxy, and that's because about 10% of the mass of the galaxy, our galaxy, the Milky Way, or really any galaxy so far as we know, will be hydrogen gas. So some of it will be in the excited state. It de-excites and emits this 21 centimeter radiation. And that, of course, is a radio signal, and you can detect it. Okay, so the numbers here are kind of interesting. I said an atom in an excited state will eventually de-excite. It turns out the mean time for that transition is 10 million years. It's a very weak, slow transition. Furthermore, the density of hydrogen in interstellar space is very low. It's about 1 atom per cc. I compare that to, say, just take your thumb, that's about a cc, and it will have about Avogadro's number of order 10 to the 24th hydrogen atoms per cc. So really very, very weak signal, very low density of hydrogen, yet you see a good signal, and that just tells you what an immense place the galaxy is. It's just, by volume, it's just huge that you get enough hydrogen to lead to a detectable signal. All right. So not only do we see the signal, but it turns out that there's a lot of information contained in it. We can look at its Doppler shift in particular. So think of this signal as being kind of a cosmic whistle. The whole galaxy is out there whistling with a frequency of 1420 megahertz. All right. So the hams will know about, or at least hams who do Earth, Moon, Earth, or satellite stuff will know about the Doppler effect. Basically, if you're looking at a cloud of hydrogen that's not moving with respect to Earth, then you'll see the signal pretty close to the expected frequency of 1420.4 megahertz. If, however, that cloud of gas is approaching you, you'll see it Doppler shifted to a higher frequency, just as the siren from an approaching ambulance appears at a higher pitch. When that ambulance passes by, it shifts down to a lower pitch. Race cars do the same thing. As they zip by, they go, many, many examples of this. So approaching things give a high frequency, receding objects give a lower frequency. And in fact, what you can do is you can take the frequency information and translate that into a velocity. So not only do we detect the presence of hydrogen clouds, we can tell their velocity with respect to us. Okay, so here is a fully processed 21 centimeter spectrum. I showed you that little nub on top of a big noise signal. Here what we do is we subtract off the noise or divide out the noise, and we end up with a signal just from the hydrogen. This particular peak, this is really a spectrum. Right? I could have calibrated this in megahertz, but instead the scale is converted to Doppler shift. So you can see that this particular cloud of gas has a Doppler velocity of minus 50 kilometers per second. So since this is approach velocity, that means that cloud of gas is moving away from us with a velocity of about 50 kilometers per second. Okay, so another simple measurement one can do is a 24-hour drift scan, and I show what the hams call a waterfall display for this. So plotted on the horizontal axis is this approach velocity, the Doppler velocity. Plotted on the vertical axis is time in hours, and you can see it runs from 0 to about 28 hours. It's slightly longer than a day. And in fact, at the beginning of this plot, you see an island of light up here. That same island of light appears down at the bottom. We've just come around and we're looking at the same part of the sky 24 hours later. In the middle, we see another island of light. The Milky Way is a band, from the point of view of an observer on Earth, we're of course embedded in the Milky Way. So we see this as a band of stars crossing the sky. And that band actually circles the whole Earth. So in one rotation of the Earth, you see it twice, or you see different parts of the band twice. If you've ever had the privilege of being in a very dark night in a place where there's a clear night, little light pollution, you can see the Milky Way fairly clearly, and it appears as a band of stars across the sky. With 21 centimeters, you can see it it's much easier to see at 21 centimeters. Okay, so what in some sense is more interesting to me than these islands of light that appear as the beam sweeps through the Milky Way is this little wisp of light that is always there. And it turns out, okay, so that's 24 hours, so that makes sense. That's or you can guess where that comes from, the rotation of the Earth. But a very interesting puzzle is you might think that the amplitude of that sine wave should be plus or minus 30 kilometers per second or no more than that, because that is the orbital speed of the Earth around the sun. If you look more closely, you see it's actually plus or minus 50 kilometers per second. And that has to do with the fact that the Earth is moving not only because of its orbit around the sun, but the sun itself is moving a little bit with respect to the galaxy. Okay, so that's probably enough detail on that for now. Okay, so the other thing we can do, and this is kind of a long story, so I haven't, I won't go through the details. I'd be happy to talk to anyone if they're interested. In fact, the data to do this are available if you'd like, just contact me. One thing that can be done and that we have done is we measure a galactic rotation curve. So basically, by looking at how fast the different parts of the galaxy are moving with respect to us, we can figure out what their velocity is with respect, what the rotational velocity of the stars in the galaxy is as a function of radius, galactic radius. So what we see here is we managed to, how do I put this? So one model we could use is the Kepler model. And that's this dashed line. That would be all of the mass concentrated at the center of the galaxy. Now that's of course unrealistic. We know the galaxy is an extended object, but you see it's completely different than the data we observe. The green curve is where we more realistically model the mass density in the galaxy. And that does much better, but it still does not adequately describe the data. The curve that is fitting the data really reasonably well is an isothermal sphere model, and this includes dark matter. So even with this relatively simple device, we're able to, I would call this, develop circumstantial evidence for the existence of dark matter. Okay. All right, so the other thing we can do, and this was our original motivation, is to see pulsars. So pulsars are rotating neutron stars that emit signals. They really emit them continuously in time, but there's a lighthouse effect. And that lighthouse effect causes the signal to blink on and off as time goes on. All right. So what is a pulsar? So if a star collapses, and if a star starts with something like between 8 and 16 times the mass of the sun, when that collapses, it doesn't collapse down to a black hole or to some other object. It collapses, it is a supernova explosion, and the remnant that's left is a neutron star. The amount of mass that's left is about 1.4 solar masses. This is nuclear matter, so all the atoms have collapsed, so you're just down to, well, not protons and neutrons, because the protons combine with electrons, so you're just down to neutrons. This nuclear matter is extremely dense. 1 teaspoon worth weighs about 3 billion tons. So you take something that has the mass of the sun, you collapse it down to something with roughly the size of Manhattan, and then it spins end over end once a second. It's really an impressive object. Okay, so it, through various complicated means, radiates a broadband energy. There's actually, or signal. Most of the signal is at the longer wavelengths. In fact, the original discovery was made at 80 megahertz. But we're working at a much higher frequency, 1421 megahertz. Compensating for that is the fact that with the shorter wavelengths, you can get more antenna gain. So it's more or less a wash, and we see a decent signal at 1420 megahertz. Okay. All right, so there it is. There's our booming signal. This is 1,000 turns, so roughly 1,000 seconds. The signal is not exactly booming. it sits on top of a huge noise pedestal. So there it is there. It just happens to come in around 0.2 in this phase plot. However, if we subtract away the noise, then we see a pretty decent signal here. We typically get signal to noise ratios of 20 or more for the brighter pulsars. Okay, so finally, I'll talk a little bit about moon bounce, which is the topic of today. So not too long after we got things going, we added transmit capability on 23 centimeters, the 1296 megahertz band. In particular, we have a 250 watt 1296 megahertz amplifier sitting up in the feed line. We can switch that in and out with a relay. So when we go over to transmit, the relay flips over, and instead of receiving signals, we drive a transmitted signal into the antenna. This is pretty busy, just shows the block diagram of how we do this. The receiver is a Kenwood or the transceiver, I should say, is a Kenwood TS2000X, fairly well-known ham transceiver. Okay, so we'll see. I'm always a little nervous when we demonstrate this publicly, because as anyone who's done this sort of thing knows, if something is not going to work, it's not going to work when you have a lot of people there. But anyway, we'll see how it goes. When things are working properly, which they usually do, CW is very easy to copy, and single sideband is quite intelligible. In particular, I remember one of our first contacts was with someone, I forget exactly who it was, but it was someone abroad, and I could tell that they had an accent that was not consistent with that of a native speaker of English. The audio was clear enough for that. Okay, and this turns out to be a very popular demonstration for the public. I think a lot of the radio astronomy tends to be a bit detailed, but everybody likes the idea of having their voice bounce off the moon. All right, so that is all I have to say. I'd be happy to answer questions in the time available. Thank you for your attention. Please do consider donating to InfoAge. InfoAge and the ISEC, it's an all volunteer operation, but it nonetheless takes a fair amount of money to keep it going. We need to pay the power bills, heating and air conditioning, maintenance. There's just lots of expenses associated with running a museum like InfoAge, and the dish is part of that. As you can imagine, the past year has been especially difficult because of the pandemic. So there's a link to the donate page can be found in the Zoom chat. If you just Google or go to infoage.org, there's a contribute link up top, and it will take you there. It asks you to fill in your address, but you don't actually have to do that. If you have a PayPal account, you can just go right there. So every little bit helps. It asks you to give $25. If you can do that, that's great. But $5 is also helpful because there's tremendous enthusiasm among the volunteers here, and we just literally need to keep the lights on. Okay. All right, so be happy to take questions now. You can either put them in the chat window, or I think you can just unmute yourself and call them out. N9NL has asked about the block diagram. Yeah, there are two separate antenna probes. Those are for the polarizations. For moon bounce, we just use a single polarization, at least on transmit. We can receive on both polarizations, but we can only transmit on one. We've really, to be honest, we've really not spent time optimizing that. Other questions? Okay, so let me turn this back over to Lori then, and I will stop my share.
So let me just say that Dan's explanation of what we do with the TLM-18 today is and was excellent. We use the TLM-18 today to do the moon bounce. And I am a licensed ham radio operator, KD2 OMA, and do the moon bounce regularly as visitors come to see our museum. And yes, it's kind of fun, and people love to bounce their voice off the moon. And my experience has been that they generally think about it for a moment and then decide what it is that they want to say. And usually it's something very simple like, hello, moon. And then they realize that they have this tremendous opportunity to send their voice out basically into the universe, because as waves propagate, they hit the entire surface of the moon and they overshoot the moon. So someone with the right ears that can decode the particular frequency of a person's voice hears you. And then they begin to think about what else they actually want to say. And it becomes very interesting. It's a lot of fun, but it's also a serious thing. We can see a lot of our own galaxy and beyond. The farthest object that we look at is M31, which is the Andromeda Galaxy, at the edge of the Andromeda Galaxy, and is 2.5 million light years away. And as I say to visitors who come to visit, who are maybe not as technically savvy as the people who are here today, I always say that this is something that is accessible to everyone. And that is the mission of InfoAge, to make science and history accessible to everyone. And I think that, we do the best that we can with that. And sometimes it will invite a child to learn more, who may be the scientists of the future, to discover exactly what dark matter really is. So that is our mission. That is what we do. So please consider donating. I think it's a good mission. And you never know. You never know whether it's your grandkid who will be the one to discover what dark matter is and unlock secrets of the universe that we could never have even imagined. So with
Lori, if I could just comment, something you said reminded me of something. I think I read it on a ham reflector someplace, but it's something I've always found amusing to ponder. And that is, and I made this comment about just how enormous the galaxy is. And people have been sending radio signals for a little over, let's call it 150 years, either intentionally or unintentionally. And turns out the galaxy, or it is a fact that the galaxy is 100,000 light years across, but it's very thin in the other direction. It's really a pancake or even a plate-like object that's 1,000 light years thick. The Earth the Earth and the Sun happen to sit more or less right in the middle of that in the thin direction. So from us to the thin edge of the galaxy, more or less the shortest path to the edge of the galaxy is 500 light years. So a signal that was transmitted back in the dawn of radio has made it 1/3 of the way to the thin side of the galaxy. So it just, moving at the speed of light all that time. So, the sizes involved are just enormous. And just to follow up a bit more on what Lori has said, we do the EME. Now, of course, that's not always available because the moon is not always above the horizon. But pretty much everything I talked about today, we demonstrate. Since the original setup, we've put in a much more capable pulsar receiver. We now, it's a wideband receiver. We use GPUs to process. We take about 250 megahertz of bandwidth. We calculate the fast Fourier transforms using a GPU board. And long story short, we can see pulsars very, very quickly now. We get especially with the brightest pulsars, we get a signal quite quickly. Okay, I'll
How many have you discovered, Dan?
We haven't discovered any because, Arecibo and competitors are far more capable, but we have observed, I don't know what the number is. It's probably about 20 or so. We see quite a few. And one of the things we've been able to do with the new wideband system is see the dispersion curve, which allows us to, that's how astronomers estimate the distance to pulsars, by seeing how much the signal is dispersed as it travels through interstellar space. And also there's another very interesting effect called scintillation, where you can look at a pulsar one day or one time and you'll see this booming signal, really, very strong signal. And then you do everything under basically the same conditions the next day, and you can barely fish the signal out of the noise. And this is analogous to the twinkling of stars. Stars twinkle because of constructive and destructive interference as the light passes through the atmosphere. Pulsars twinkle because of destructive and constructive interference as the radio signal propagates through interstellar space. The time scales are quite different. Twinkling, of course, is a second or a fraction of a second. Pulsar twinkling, scintillation, the time scale is sort of 15, 20 minutes. And it also varies with frequency. So you can see a very strong signal at 1450 megahertz and then just nothing at 1400 megahertz, or vice versa.
Yes. It's so good to have Dan on hand to explain the finer points of what we do with the radio telescope. Although, when people do visit us, we talk about exactly what they see, these programs that give us the information that we are looking for as we do our observation. But we are always working on upgrading the system. And recently, we actually looked at something that I don't understand well, called a maser. And a maser is a microwave emitter, microwave in size, that is. And that's very exciting. We are on our way always to look for signals that are different than the ones that we're looking at today, so that we don't know what will happen in the future. Things may expand. This 18-meter radio dish is fantastic and allows us to do great things, even though it is rather small. But it does what we want it to do. It does work. And let's see.
Lori, there's another question in the chat that I could address. So the question is from N9NL. I had mentioned that the original motivation, which is still strong motivation, was teaching. So what do our undergraduates do? Well, mainly what they do, we have a lab where they look for pulsars. So we have software that just sort of does it straight out of the box, but we ask them to, first of all, go to the astronomy catalogs, find the pulsars, figure out where to point the dish. Then we get a signal and they have to go off and do the coding for the signal processing. So that's mainly what they do. They could conduct independent research. We have not had that so much yet. These are not, if we had PhD students in radio astronomy, they would probably get time on a more capable instrument. So how do I put this? Doctors don't usually start, the first day in med school treating patients. Same thing with physicists. You have to sort of work your way up. Certainly independent research is very, very important, but there's so much that's been learned already. We like to have our students master some of that before they go on to the more advanced topics.
And Dan, if I may add, we have had students use the TLM-18 for their own research as they're writing a thesis, for example. We had students that were working with Greenbrier, and one of their telescopes was down, and they asked if they could use our dish to bounce signals from the moon to points in Europe, and we were very happy to accommodate them and to help them. We've worked with universities from around the world with the TLM-18 who might not have had a dish of their own. So we are not necessarily doing independent research, but we are helping people who are doing independent research.
Yeah, and I should mention that we're basically open source. If anyone in the audience wants to use the dish for radio astronomy, we can take data for you and provide tools to analyze it. Working out this rotation curve is a tremendous exercise. One really learns a lot by doing that. And it's not, this has been done before, obviously, but it does take you right up to the forefront of modern research. Oh, I see. Actually, sorry, I ran over. I didn't realize.
Yeah, so let me go ahead and take over now. Can everyone hear me? Am I being heard?
Yes.
Okay, great.
Yes.
So let us begin. I'd like
Lori, maybe you're going to, sorry, no, go ahead. Never mind.
I'm going to go ahead and introduce Ray Chase and Al Klase. These guys are fantastic. Their careers have been exceptional. And now as they work here at InfoAge to do research, historical research in particular, they have found some information about what Edwin Armstrong did to create the transmitter that made it possible for the moon bounce to have happened in 1946. So please let me turn over this meeting to Ray Chase and to Al Klase. And can you please unmute yourself? I'm going to go ahead and unmute you.
Well, I was able to unmute myself. I assume you can hear me.
I can hear you. I'm asking Ray to unmute himself. Ray, can you unmute?
Yeah, I'm muted. I'm fine. I can hear everybody.
Okay, you guys go ahead and take over.
Okay, I'm the primary presenter, so I will need to share screen.
Okay. Here we go. I just want to warn you that if a participant comes in, you'll receive a message to admit them. Please admit them. Okay?
Roger.
Here. It's all yours.
Okay. Okay. My name's Al Klase. I'm N3FRQ. I'm a member of the New Jersey Antique Radio Club, and in turn, we're a supporting organization for InfoAge, and we run the Radio Technology Museum on the main campus here at InfoAge. Today, I'd like to talk about our favorite radio inventor, Edwin Howard Armstrong. He was born in New York. A few years later, his family moved up to Yonkers, nice big house. When he was about 10 years old, his father was in publishing, brought home the Boy's Book of Inventions. And Howard read about Marconi in there, and it inspired him to a life in radio. He went so far as to build a 120-foot mast in their backyard, flew kites to hold up antennas and such. And eventually he attended Columbia University as an EE student, rode down there on a red Indian motorcycle on a daily basis. Now, most of what we're talking about today depends on vacuum tube technology. I mean, today everything is transistors and integrated circuits, but this was the electron device technology of the day. And in fact, in Armstrong's day, it just barely existed. A guy named Lee DeForest had invented the 3-element vacuum tube. You have an evacuated glass tube. You have a hot cathode at one end, plate at the other end, battery outside and a load, so you have a current flowing here. And Armstrong's addition to this technology was known. There were things like it was known as the Edison effect, but Armstrong's addition was to put a grid in here. And so when you put rather DeForest contribution, so a small signal on the grid will either encourage or discourage the flow of electrons. And what this does is control energy from a local battery, so you can make a small signal into a big signal. this was very primitive at the beginning, but on through the years, this becomes the basis for radio and television and computers until the transistor is finally invented. So in 1912, Howard gets a DeForest Audion, and he builds a radio out of it. And there's sort of a block diagram down here. You have an antenna and a tune circuit, and the Audion, which is a detector and an amplifier. And what Armstrong developed was a circuit where he added feedback from radio frequencies from the output of the amplifier back into the input circuit. And what this does is, if you look at this schematically, you've got some resistance out there, which is unavoidable, but the energy coming back cancels out the resistance, and the response to the circuit gets better and better as you increase the amount of feedback. You get to a point where the resistance is completely canceled out, and then the circuit oscillates, becomes a transmitter, a generator of radio frequencies. So this resulted in a superior radio receiver. It was 20 or 30 dB more sensitive than the DeForest Audion, just in a simple circuit. But perhaps more important, it's the first electronic oscillator. And that allowed a couple of things. First of all, it allows heterodyne detection of CW signals, which was very difficult to do before this time. People would be running Alexanderson alternators to be the BFO in their receiver. It also allows you to build a small and portable and practical continuous wave transmitter. So this is the beginning of the end of spark telegraphy and really the beginning of the electronic age. Now, there's a tie into info age here. In 1914, Armstrong had his patent in place and was revealing the feedback circuit to the world. And he ends up doing a demonstration to the Marconi company. Their big receiver site was now the InfoAge site today, Marconi Belmar. And he goes down there to do a demo, and the person that Marconi brings in to be their radio operator is David Sarnoff, who later becomes a big wheel in the Radio Corporation of America, which is established later on. The site was under construction. There's a picture down here at the bottom from 1914. This was the operations building, but it was under construction. There was a construction shack outside, and Armstrong and Sarnoff sat there all night playing with Armstrong's radio, which was far and away more capable than the Marconi radio they were comparing it to. The two men became fast friends. Now, a couple of other things that happened in that particular time period. He also does a demonstration to AT&T and their chief engineer, J.J. Carty. AT&T took a formal disclosure from Armstrong, and they went silent on him. They went off and invented modern radio. Guys with names like Heising and Colpitts and Hartley did their thing. He also became locked in a long-term battle with Lee DeForest, the inventor of the Audion. DeForest, of course, claimed that he invented the feedback circuit, which of course was completely bogus. So the feedback circuit ultimately leads to radio broadcasting. KDKA in Pittsburgh goes on the air at the end of 1920, broadcasting the election results. Radios in the home become commonplace. In fact, this is a Westinghouse Armstrong licensed regen, ladies listening here. But to use a radio like this, you had big antenna in the backyard. But this just became a complete fad. Everybody had to have a radio. So shift gears a little bit. war clouds are gathering. We United States enters World War I in 1917, and there was a lot of patriotism afoot here, and there was also elements of the industrial military complex. The phone company was going to sell a lot of stuff to the Signal Corps, and J.J. Carty, who we mentioned, puts on a uniform and becomes the chief signal officer, and he recruits thousands of people out of industry to join the military and support the technology there. And one of these people, and I don't know if there was direct personal contact, but Armstrong at this point was fairly famous for the feedback circuit, not rich, but famous. And he and Carty knew each other. Armstrong volunteers. He gets a letter, says, effective immediately, you're captain in the Signal Corps. 2 weeks later, he gets another letter that says, go over to Hoboken and get on the ship. You're going to France. And in France, Carty had helped set up a thing called the Division of Research and Inspection. They rented a mansion in Paris that had some space behind it. He put $100,000 in lab equipment in wooden crates that could be made into workbenches. And so in effect, what you had was an AT&T research laboratory in Paris, where Armstrong was assigned to be the head of the aircraft radio section. And while he was there, he solved a number of problems, but one of the problems was high frequency reception. The existing technology, was hardly good to a megahertz. And they wanted to do some work up around 3 megahertz. They thought maybe they could detect enemy aircraft by listening for their ignition noise. And so what Armstrong comes up with, he leverages his knowledge of heterodyne frequency conversion, which of course he was familiar with from the regenerative receivers. But instead of converting the incoming signal down to audio where you could hear it, he converted it to a lower radio frequency, ran it into a French amplifier and filtered it at 100 kilohertz and created a really sensitive radio. He named this the supersonic heterodyne receiver. In the old days, they used the word supersonic the way we would use ultrasonic today. So this is the super heterodyne circuit. And yeah, we're still using this technique today. You're carrying around about 4 of these in your cell phone. So on into the 1920s, Armstrong comes back to civilian life. He's hypothetically working at Columbia. And his old buddy, David Sarnoff, buys his super heterodyne patent and another patent for a whole bunch of money, makes Armstrong rich. Armstrong also courts Sarnoff's secretary, Marion McGinnis. There's this famous episode of him clowning around on an RCA tower and sending the pictures to Sarnoff's office. And he is working with RCA to develop the first commercial super heterodyne receiver. And he gives the prototype of that to Marion as a wedding present. By the way, a good read on Armstrong and Sarnoff and DeForest is the book Empire of the Air. If you haven't read it, do so or see the video. Just quickly, here's Marion and Howard on the beach with the super het. And the important thing about this radio is it was sufficiently sensitive that it could operate without an external antenna. There's just a loop in the back of that box, works just fine. It's a portable, you can tell it has a handle on it. Of course, it weighs about 40 pounds, loaded down with batteries. So that was a great success for Armstrong, his second great invention, the super het. And moving on into the 1930s, he develops wideband frequency modulation. Now, there was a lot of AM activity, a lot of CW activity, but a persistent problem with AM was in old terms static, lightning, and there was a lot of man-made noise. I mean, every automotive engine put out a lot of ignition noise. There was no suppression of that. And simple electric motors with sparking commutators did the same thing. So Armstrong does a lot of work to develop wideband frequency modulation, which beats the noise. No static at all, as the Steely Dan song says. And it does a couple of things. In addition to getting rid of the noise, this happened at high frequencies up in the 40, 50 megahertz range for starters, wide bandwidth, and that allowed high fidelity transmission, which would eventually take in stereo. He did his early experiments about 1933 from the RCA experimental TV transmitter site on top of the Empire State Building. However, his relationship with Sarnoff turned ugly. So in 1935, he went off and built his own laboratory and radio station. By the way, this is guys from GE about 1940 demonstrating their FM radio in front of this huge spark, and they managed to clearly hear FM signals, while of course AM was completely wiped out. So Armstrong's facility at Alpine, now Alpine is in northeastern New Jersey, right by the Hudson River. This is, if you know the area, this is 9W here. The site is about 500 feet up out of the river. He builds a 450-foot tower so he could put a big signal down into the New York City area from here. Nice brick laboratory and transmitter building down here at the bottom. So FM changes home radio once again and brings hi-fi sound into the home and encourages the whole hi-fi phenomena. So FM's becoming a going thing, and then World War II breaks out. And so a lot of things just sort of go on hold. But Armstrong, and remember it's Major Armstrong, he has a strong feeling for the Signal Corps and such things. He'd been actively working with the Signal Corps on FM two-way mobile radio since about 1939. That was based on some work he'd done with the Link Corporation, building radios for the Connecticut State Police. And this development leads to the best mobile radio system of World War II, which turns out to be really important when you're talking about mechanized warfare. FM was also used for carrier multiplexed radio relay systems. You put multiple telephone circuits down a single radio circuit and save a lot of trouble there. He signed his patents over to the Signal Corps and the government for war purposes. And he took a contract to develop FM radar. He thought he could extend the range of radar using FM techniques based upon the range and noise resistance he was getting out of the wideband FM broadcast things. So this is the building at Alpine. The big tower is off to the right here, but he installed a SCR 271 Army radar tower there, an antenna, and built electronics to implement his FM radar scheme. Now, just a quick review of radar. You have a directional antenna, and you send out pulses, and you listen for the echoes. Typically on an oscilloscope, here's the main bang, the transmitter pulse, and sometime later over here, you get a reflection from the target. In normal pulsed radar, these pulses are very narrow, and the duty cycle is considerably less than 1%. So the amount of energy involved is limited, and that places some limitations on how well your radar can work. We don't know a lot about Armstrong's FM radar. It was a classified project. It was during wartime. And what we do know comes from his patent application from 1947, which was really pretty thorough. You could almost rebuild one of these from the patent application, but who would really want to? I threw the block diagrams in here just sort of to point out each one of these blocks represents a vacuum tube and the support circuits to go with it. So this thing was fairly complex. And what he used in the transmitter was sort of the same wideband FM scheme that he used in broadcast, except it was modulated by a variable audio oscillator and keyed on, and the transmitter was keyed on and off on alternate cycles of that modulation. And now so he had a fairly large amount of energy going out with a 50% duty cycle. And then to improve the receive situation, he built a very narrow band receiver. In fact, a quadruple conversion superheterodyne. We'll talk about that in the next slide. And it's frequency locked to the transmitter. It gets its local oscillator signals from the transmitter. So here's how it worked. Here we have frequency and time. Of course, in an FM transmitter, you have a carrier frequency, and the modulation changes that frequency one direction and then the other. And in this case, it was 200 kilohertz in each direction. This was quite a wide signal. So he turns the transmitter on for one cycle of modulation, turns it off for a cycle, back on for a cycle. So if you have this transmitted signal hitting a target that the return time is the same as the cycle time here, when you turn the transmitter off, that received signal will be here sort of following the same path. And his receiver, which is very narrow banded, tracks that frequency. So case A here, where the target is one cycle out, one cycle distance, the receiver hears it. If the target is not at that distance, the receiver doesn't hear it. So he hoped that between high average transmitter power and narrow receiver bandwidth, he'd be able to extend the range of radar. Our analysis of this is that this probably worked, but it's subject to some serious limitations. One is that you still have the problem that you're working with line of sight. So you can't see down over the horizon with it. So you don't have a great advantage over advanced pulse radar. And also, the operation was probably cumbersome because apparently you had to tune that audio oscillator for the modulation. Is there a question? You had to tune that audio oscillator to find the target. So target acquisition was probably really slow.
Right. Well, this afternoon, I'm going to look online and see if there's any more information.
Maybe tonight something will come out.
Hello, there's someone out there who is.
Yeah, it's I think it's Alan, Lori. Lori, if you make me the host, I can take care of this. Sorry to interrupt, Klase.
Yeah, that's okay.
Interruption, not sure what that is. Hold on.
So anyway, the Signal Corps pretty much dropped this project after World War II, and there's a lot of confusion about Armstrong's relationship to Project Diana. We'll go into that here and try to straighten some of it out. There's pronouncements that that the moon bounce was done with FM radar. No, that isn't true. Yeah, and Armstrong FM radar died out. There were later radar systems that used FM techniques, but they were distinctly different from what Armstrong was doing. So one of the first issues we had to face was there actually Armstrong radar at Camp Evans at the Diana site? And because we looked at all the contemporary articles on the moon bounce and the word Armstrong never appears. A little later on, Dr. Harold Zoll, who was director of research at Fort Monmouth and one of the real heavies in radar development, wrote a book called Tales of Government Scientists. And in there, he says in so many words, Major H. Armstrong had been working on a very high-powered radar set, which was set up in the Evans area at Fort Monmouth. And then he mentions that Jack DeWitt later on modified it to do the moon bounce. So we know that we're taking that as fact. And so it was Armstrong equipment. Let's take a look at John DeWitt. Interesting character. Guy was a ham radio operator since 1921. He's about 15 years old. This was in the Nashville area. He gets an EE degree from Vanderbilt University. He works for AT&T for a while. And then he goes to work for WSM, the big AM station in Nashville. Think Grand Ole Opry. And he also had a side interest in astronomy and ham radio, of course. And the date I had was 1940, and it was interesting to see those pictures of their attempt at moon bounce in the late 1930s. So he's thinking about and actually trying to do moon bounce. War breaks out. He joins the Army. They make him a lieutenant colonel because of all his experience and capabilities. And he eventually becomes the director of the Evans Signal Laboratory, which is Camp Evans and the Diana site. And so now the war's over. He wants to do moon bounce, and he runs the Army Radar Laboratory. So, you know, what an opportunity. So is born Project Diana. Diana is the Roman goddess of the hunt and the moon. I had a lot of trouble finding a picture of Diana properly attired, but there she is. And this was mentioned a little bit earlier, but the basic team was Colonel DeWitt as leader and King Stadola as chief scientist, Harold Webb, Herbert Kaufman, Jack Moser.
Toddler.
I'm sorry?
Toddler.
Thank you.
Yes.
I need to get straightened out on that. There's an old Czech folk song where it's Stodola Pumpa. Stodola means barn in Czech, but that's another story. So that was the team. And Dr. McAfee gets involved in this because, of course, he's the master of things like the radar equation. And there are several factors that go in here, like transmitter energy, receiver sensitivity, how good your antenna is. You can't do much about target reflectivity, but maybe you want to calculate that out. Now, the basic problem here is you're fighting what's called the inverse square law. Signal comes out a mile and its energy is distributed across some area, comes out 2 miles, now it's distributed across 4 times the area, 9 times, etc. And now this happens to you twice, once going out to the target and again coming back. So we end up with this thing being a fourth root in here, which means any change you make here is going to be real tiny. You're going to have all your ducks in a row to make this work. So energy is power times time. So you want to keep the transmitter on as long as you can. And part of receiver sensitivity is also its selectivity, so you don't have to listen to the noise. So those were the problems. So how did they do it? Well, to maximize the antenna gain, they already had the SCR-271 radar up there, but they put a second antenna side by side. That gets you 3 dB improvement in the antenna. They needed high average transmitter power. Now the pulsed transmitter in SCR-271 wasn't even going to come close. But they had Armstrong's transmitter sitting there that could do 4 kilowatts CW. And so long pulses weren't going to be a problem there. It's also crystal controlled, so frequency accuracy is going to be good. And they had Armstrong's narrow band receiver, so they could go to narrow bandwidth and beat the noise. The receiver has to be accurately tuned to the transmitter, but Armstrong's already was. They made some modifications to it so they could tune it plus or minus 300 hertz to take care of Doppler shift. So that's what they do. Now, this scheme was going to be pulsed radar. FM had nothing to do with it. They disabled the FM modulation in the transmitter. So here's the classic picture of the Diane antenna looking at the moon. The individual elements were, this is 110 megahertz, so the elements were so big. And the basic SCR-271 was an 8x4 array of dipoles in front of a reflector. And they hung a second one up here, making it an 8x8 array. So that's a 3 dB improvement, which doesn't sound like a lot, but it's the same as doubling your transmitter power. This is almost the only piece of SCR-271 they actually used beside the antenna. This is the control console, which involved the antenna control dials and controls there. And this was kind of haywire. You see a lot of extra stuff hanging around here. The transmitter was a pretty easy modification to Armstrong's transmitter. Typical Armstrong FM, you start with a low frequency crystal oscillator, about 500 kilohertz, and you multiply your way out to, in this case, 111.5. And so that's out to your transmit receive switch. And this signal also comes out to control the radio frequency. Got some pictures here. You see Herb Kaufman adjusting the high level multipliers in the transmitter, and here's Jack DeWitt, taking a look at the transmitter. Now, this was another source of confusion. The actual transmitter appears to have been the Armstrong transmitter. And we know this from some of the articles that were published in 1946 by the members of the team. This was Mofensen in electronics in 1946. And we see that the output amplifier uses vacuum tubes called 6C21. And they look like this, and that is indeed what's in this box here. And that'll get them about 4 kilowatts output. And that's what they used for the initial experiments early in 1946. Now the confusion comes in because shortly thereafter, they decided they wanted more transmitter power. They did take an SCR 271 transmitter, which has a pair of water-cooled triodes in it. However, the transmitter was a free-running oscillator, and that wasn't going to work for moon bounce. So they modified it to be an amplifier and attached it to the output of the 4 kilowatt amplifier. And this data comes from proceedings of the IEEE in March 49. So the output of the transmitter was increased to 15 kilowatts. I know there's a reference somewhere that says 50 kilowatts, but that apparently wasn't the case here. And a lot of the confusion arrives because here in April of 46, where DeWitt appears on the cover of Radiocraft magazine, he's in front of the SCR 270, the modified SCR 271 transmitter. So, you know, there are accounts that say that's what they used for the initial experiment. We don't think so. That was later on. The receiver, quadruple conversion super heterodyne. Now, to go back to the super heterodyne, signals come down from the antenna, they get to a mixer, which is a non-linear circuit, and you inject a local oscillator signal, you get beat products that come out over here. And usually you take a high frequency, you convert it to a lower frequency, a fixed lower frequency, where it's easier to amplify and filter it. Now, you can't go all the way down to a very narrow bandwidth, at least in those days you couldn't directly. So we make 4 frequency conversions. First intermediate frequency being 32.5 megahertz. They got a bandwidth of a megahertz there. Second conversion gets you down to 6.7 megahertz, about 200 kilohertz bandwidth. Third, down to 6.5, maybe 50 kilohertz bandwidth, and then finally all the way down to audio to 180 hertz with a 50 hertz bandwidth. So these first 3 conversions, the local oscillator frequencies are derived from the transmitter. So this thing tracks the transmitter. Now, they had this problem of Doppler shift because the moon has a velocity relative to Earth. I think it's maybe a couple hundred miles an hour. And with a bandwidth this narrow, you have to compensate for that. So this 4th oscillator was again a crystal oscillator, but it was variable. They had a crystal holder that could change the capacitance of the crystal. And so they could tune about plus and minus 300 hertz here to be precisely on the return signal. So all of that put together, well, here's Stodola and Webb. Webb has his hand on the fine frequency control for the receiver. We weren't real sure just what this stuff was or what it looked like, but this is a picture of some Armstrong equipment that the Columbia people have. This stuff was at Alpine. It was really unidentified, except that this was a transmitter, this was a receiver. But if you look at these doors here and these doors over here, this sure looks like the Armstrong receiver as Armstrong built it. And like I say, there's the crystal holder with the variable frequency to do the fine tuning. So 10 January 1946, they have their first success. Here was a picture off their long persistence 8-inch oscilloscope. Here's the trailing edge of the quarter-second pulse here. I guess they had some local reflections here on Earth, but 2.5 seconds later, they get a nice pulse back from the moon. So they did the job. And as somebody pointed out earlier, these QSL cards were from later on. They continued doing moon bounce experiments on through the 1950s with more power and higher gain antenna, et cetera, et cetera. And at some point, they started issuing QSL cards. But so Project Diana moon bounce experiment did not use FM radar techniques, absolutely not. But it did heavily depend on Armstrong designed hardware. One last slide. Meanwhile, back at Alpine, and this story comes from a gentleman named Ren McMahon. He later becomes famous at CBS, but he worked at Alpine in the late 40s. And he recounts that this was an audio recording while he described some color slides he had taken. And he says that REL, that's Radio Electronic Laboratories, they're out in Long Island, they were closely related to Armstrong, was busy building a copy of the transmitter we have over here. That transmitter Armstrong paid for and gave to Fort Monmouth, which gave it to, there's something signal laboratory down there. That would be Evans Signal Laboratory. And then Ren tells the story, and so it's possible that while the modifications were going on for Project Diana, that they were working with the Alpine people to get the modifications made properly, and the system at Alpine may have been modified in parallel. However, Ren tells the story that he suggested to Armstrong that they range the moon. And he says Armstrong was usually a pretty easygoing guy, but he got real stern, and he says, Rennie, we're not going to do that here. Don't aim that thing at the moon. Don't let me catch you doing it. And so Major Armstrong was leaving all the credit go to the Signal Corps. And that's pretty much my story, and I'm sticking to it. Let's see, I guess I'll stop share. Well, let me keep share up in case there's questions that involve some of the slides, but if there are questions, I'll take them now.
Remember to unmute yourself if you have a question that you'd like to ask instead of in the chat area.
May I ask a question about why they chose a frequency of around 100 megahertz rather than a microwave frequency where they could create a much narrower beam by the Fresnel limit?
There just wasn't any appropriate equipment in those days. It was kind of a struggle to get up into the 600-700 megahertz range during the World War II period. And I think part of the thing here was that the Armstrong equipment and a reasonably high gain antenna were sitting there, and so that's what they did. Later on, they moved to higher frequencies for further experiments.
Didn't they have magnetrons and klystrons?
Let me
Yeah, Ray, go ahead and address that.
Let me address that. Yes, later, certainly in the 1945 period, they had very high power magnetrons, and they could have done it at microwave frequencies all the way up to 3 centimeters. But remember, they had an antenna, and that was available to them, but that only worked at around 100 megahertz. Remember also that you look at the radar equation, they needed a lot more sensitivity than existing receivers could give you. The noise level of existing radar receivers was up in the 10 dB range, and they needed a lot of receiver sensitivity. They also need the tight frequency control to compensate for the Doppler shift. So yes, they could have done it at a higher frequency, but they just didn't have the types of receivers and frequency control, and they had an existing antenna. So that's why they did it at that frequency. You got to remember that this was kind of an off the book project by Colonel DeWitt, and the Army was kind of embarrassed when they were successful because this wasn't a high level project, but it became a high level project as soon as it was successful.
Thank you. Very good answer. I appreciate that.
Anything else? Okay, we'll get
Al?
back. Yes.
Mike Molnar, I know you and Ray know that I've been doing research on Armstrong and FM, and you've answered the questions that I had in your presentation. It was very good. I did want to contribute that where Armstrong didn't want them fooling around with it at Alpine, it was just, to me, from what I've been researching, his personality would have been that he wouldn't even want false attribution to him if it wasn't his circuitry being done or his continuous wave plan.
You're very right, Mike. That's exactly the kind of guy he was.
But thanks for a great presentation.
Hi, I have a question. First of all, great day and great talk so far. Looking forward to the rest of the day. I was just wondering, I had heard that they were worried, and I don't know who they was, but it, could have been the military or even Armstrong, that the moon could explode if a signal was directed at it. I'm glad it didn't happen, but could have been the end of the planet. But really, did they really wonder about that? Because
I don't. And Rebecca, good to see you. But
yeah,
I don't think any reasonably scientific person would even consider that. Of course, the A-bomb people were concerned that they'd start a chain reaction in the whole atmosphere. So who knows? I guess you can always worry about something.
And there are moons that are liquid filled, like even some of Saturn. So who knows? I mean, we're just lucky it didn't happen. But
It looks pretty rocky to me in a telescope, so I don't think I would have worried about it.
yeah, true.
Put that in the same category as the green cheese.
Right, exactly. I'm also very impressed. Dave Saul and I were chatting privately on the chat about, they were using slide rules that they could figure out all this math. That's really pretty impressive. So.
Okay, folks, let me interrupt here. We are about 5 minutes away from the moon bounce to commemorate the original moon bounce. We're going to try to do it at 11:58. And I want to give you an idea of what this means today. As I said before, I press a couple of buttons and we're on the moon. And when it comes time to do the moon bounce at 11:58, I would like everyone to scream as loud as possible into your computer so that everyone does bounce their voice off the moon. And then we can try to do individual moon bounce. We have a limit in our particular Zoom meeting of 100 people. It is possible to start a second meeting or for you to email me at lauber@gmail.com, and I will put my email address up before the day is over. And then that way, if you would like to Zoom your voice over, to the moon, over Zoom rather, you can do it at any time. I will set it up as long as the moon is available, because when the moon sets, that's the end of our ability, and the moon isn't always cooperative. It was cooperative today on January 10th, 2021, and we're lucky to be able to do this. Thank you, Moon. I want to show you what it takes to do the moon bounce today. So here's the console. I hope everyone can see it. Can everyone see the console? So we've got 2 separate systems that control the situation. One of the systems actually moves the telescope, and that is where I enter the coordinates to move the telescope. And then the next system which is here and not up and running, but it will be in a second. Is the system that actually does the sending and receiving of the signal. These systems were built by Princeton University. The telescope moving system was built by Norm Jurassic, and the radio, of course, by Dan Marlow. What I've got up is a UHD FFT window that gives me the information about the strength of the signal and the frequency of the signal that I'm sending, and the frequency of the signal that I'm receiving. Now, the thing about it is that this tells me that I need to calculate for the Doppler shift, but we can overcome that easily. So here we go. It's 11:56. The moon is being servoed. I don't know if you can see the top of the screen here, where our star plotter shows you where the moon is. It's just about 10 degrees above the horizon. And I think that we'll be successful. Let's set it all up.
Hey.
Kenwood T2000 as our ham radio, and as everybody knows who's a ham out there, this is regulated by the FCC. I need to send my call letters. When I do, and after I send my call letters, anyone in the room and the Zoom room, I suppose, can send their voice to the moon. So here we go. The very first time that EME has been done via Zoom. Okay, let's first send a CW.
Tell everybody to unmute themselves.
Please, everyone, unmute yourselves.
How do we do that?
Lower left.
Stand by.
We're back in.
Okay.
Chaotic modulate.
Please keep quiet until.
Do you want to hear them people calling to the moon?
All right, everyone, just stop talking for one moment. Here we go. It's 11:58.
Oh, now, brown cow. Oh,
McAfee gods.
God's peace, love, and grace to all mankind.
The trick is that you have to be quiet immediately after you say whatever it is that you're saying, so that you can hear the echo, you can hear your voice bounce. So everyone yell hello moon at the same time at the count of 3. Let's try it. Let me try first.
hello,
moon.
hello, moon.
I didn't catch it. This is Katie. Hello, Delta 2, Oscar, Mike, Alpha, sending. Cruise first time. Here we go.
Hello.
Hello, moon. You're
God
muted.
bless America.
Hey, Lori, unmute.
Can you hear me now?
Yes.
Wonderful. Did everybody get to send the signal to the moon?
No.
Yeah, Lori, I don't
Yes.
think this is going to work so well with so many people.
It worked well from here. I heard everybody's voice and I heard the return. Okay, does anyone want to say something specifically to the moon at this point?
Yes.
Go ahead.
Yes.
Golf 4 Bravo X-ray, David.
Yes.
We love
QRZ
you.
from AA6EG.
A hello message from KE8.
God bless America.
God bless America.
Ditto.
To a better 2021.
Delta.
Hello, Moon, the Moffinson family.
Say it, Maeve.
Greetings from K3 RPM.
Say it again, Maeve.
Golf 4 Bravo X-ray Denmark.
Peace on Earth
No
for
to the
everyone.
moon from Miss and back.
McAfee. GM8BJF.
Yell it out,
Dr.
Maggie?
Marlow is telling us that this isn't working, but let me just say, I have heard the echo return for every comment. I've said. That was great, you guys. Thank you so very much, everyone, for participating. We are now, waiting to do the moon bounce individually. At 12:15, Cindy Pomerleau will speak. She is the daughter of Dola, and she will be talking to us. Everybody mute, please. So we can either take a 15-minute break or individually, if you'd like to do the
Hold on a second, Lori. Let me mute everyone. You'll have to unmute when I do that.
Am I muted?
Okay, unmute now, Lori. You have to unmute, Lori.
Is everyone
Yeah.
unmuted?
Go. No, just you unmute.
I am
Good.
unmuted.
Go ahead.
Hi. So anyone who wants to do the moon bounce individually, raise your hand and I'll go ahead and let you do the moon bounce. You should be able to hear your echo. Okay, here we go.
Okay.
Lori, excuse me. Lori.
Okay. Peace on Earth for everyone and also in the galaxy.
Do that again.
Peace on Earth for everyone and the galaxy.
Did you hear it?
No.
Yeah, Lori, I think this is not
More time. Thanks, Dan. Yes.
not working so well.
One time.
Should I try it again?
Yes.
Lori.
Peace on Earth for everyone on Earth and in the galaxy.
Lori.
Long and prosper.
Did you hear it?
Lori.
Yes.
You are not getting. Turn up the audio. No one's hearing the audio from you.
Yeah, I think the problem is the radio has to be closer to whatever speaker or whatever microphone you're using.
Bring them near your speaker and just turn it up. The echoes will be good enough.
Yeah.
Just
We have a lot of noise as well, so.
Turn up your audio to the point where you hear noise, where all of us can hear noise from the receiver.
Just send a CW signal for a minute if you can, and we'll tell you when we can hear it.
But if you can hear the noise, hello? I don't think I'm getting it. You hear the noise from the receiver? Turn up the noise from the receiver.
Did everyone hear that?
No.
Yep. Barely.
So.
Yeah, try the noise. The noise is a good idea.
We're not hearing anything in the UK.
Can you hear that?
No, unfortunately, I think Zoom defeats you here. It has all kinds of noise canceling.
No. Just
you may be
can you
impacted
turn up
by
the receiver so you can hear it? Hear it, Lori? Turn the gain of the receiver up. Turn the I don't know if I'm
the audio.
I can hear your moon bounces perfectly here.
Yeah, Lori, the problem is that whatever microphone you're using for the Zoom is not close enough to the radio.
Yeah, I'm putting it right next.
Oh, okay. So turn up the noise on the, turn up the audio on the receiver.
Go.
There, we can sort of hear it.
Hello?
Yeah, please, everyone just stand by. And Lori, maybe send some CW if you can.
OMA, Kilo Delta 2, Oscar Mike Alpha.
Oh, there we go. All right. I think it's just going to be hard for people to do this. It's too many links involved.
Right.
but
understand.
we could hear Lori's voice coming back from the moon there. Where are we in the
Turn up
program?
your audio any further. Just turn it up as loud as you can get it from the receiver. Turn up the audio as loud as you can get it.
The AF gain.
We should be able to hear the noise from the receiver. Be able to hear the rush
The
from the
noise is
receiver.
filtered out by the system. The Zoom
cancellation. Here we go. Hello, moon. Hello, moon.
All right, heard that.
You heard that.
Did everyone hear that bounce?
I heard it. It was garbled.
You heard your voice, but you've got a Zoom problem.
Yeah. Zoom is thwarting us with its noise cancellation.
There is an option to turn off the noise cancellation.
Ah, let's see.
Called original sound.
See if I can make that happen.
I think the Zoom system filters cancel the noise. That's why we don't hear it.
Yeah.
Right.
I'm looking for that setting. But,
too.
And you also have echo cancellation things happening if more than one person is talking. And so that mutes other stuff.
Well, everyone who is here and can hear me, obviously you can come to ISEC.space. You can come to ISEC at 2300 Marconi Road when the moon is available and do the moon bounce here. And I think
COVID is gone.
yes. Yeah.
Some of us are a rather long way away from you.
I know. Make it a trip. We have a beach close by. In any case, I did hear everyone's voice hit the moon and bounce back. And if we understood Zoom a little bit better, I think that we would have, you would have heard your voice as well. It's all recorded. So the entire meeting is recorded. So the bounce back that I heard has been recorded. And it will be on ISEC.space. You will hear yourself in that recording.
You know, suggestion in the future, it might be good to record the return and then play that back. Because when everyone was trying to overlap, they were really just getting in the way of the hearing the return, you know?
Sure, I understand. That is exactly what happened. The output frequency is, let's see.
Read it off the radio.
1296, you know, but sometimes.
020, isn't it?
Pardon me, 020, 1296, 020. But it varies when I send it. So let's, I'm going to turn it down and tell you exactly what I got. On CW. Oh, there it is.
Yeah, Lori, I think just to demonstrate it clearly for people, if you just send a string of dashes on C, you'll hear them come back.
String of words to demonstrate how it's supposed to work, how you want it to work.
It's a little hard to tell what's send and what's receive. You have the monitor on?
Laurie, say some words and let them bounce back. So we'll see the way it's supposed to work.
If you can't hear CW, you'll have a, yeah, actually, why don't you look at that here? This is there's transmit. And there you see this peak in the spectrum for the reflected signal. And then it dies away. There's transmit. And those spikes remaining are the receive signal.
C'est ça, c'est les oreilles. Bien, c'est bon. C'est trop fort. Non.
Yeah, that was a reflection you heard there.
Lori, I can hear it clearly.
Yeah, it may vary from client to client.
I was going to suggest that she send 3 DITs for historic reasons.
Well, there it is, folks. This is what we do. We bounce people's voices off the moon. Yeah. We did not set up equipment to hardwire into the Kenwood so that you would hear that signal directly from the radio. But yeah, but it's all recorded, so I think that I will be able to hear everyone's moon bounce. Please email me at lauber@gmail.com, and I can do this for you individually as well.
By the way, do you hear me? This is Pat.
I hear you, Pat.
This is a good illustration of how difficult it is to do anything for the first time on moon bounce.
Yes.
It is so many things that have to be precisely correct. And it could be just a little switch, a microphone, the antenna could be a little bit, even a tiny bit off. And you got to figure out why it is that you're not hearing your moon bounces. And this is a really good illustration of how tough that is.
Yeah, you know, the interesting thing is that here at ISEC, it's working perfectly. I hear everything. However, Zoom is getting in the way.
Yeah, right. I appreciate your comments, Pat, but I think the challenge here is not the moon bounce. That actually works pretty easily. It's Zoom.
That's right.
Moon bounce is easy by comparison.
And I think that's why the recording is going to be very interesting, because you'll be able to hear everything that's gone on in the recording. And so you'll hear the return. I hear it clearly here. Yeah, but thanks, Pat. You're right. The first time
what I was saying was the first prototype of your test of your station, there will be a half a dozen things that aren't what they seem to be. And you got to figure out which ones have to be adjusted and whether your antenna's pointed right and a gazillion other things that have to be precisely right.
That's right.
That's part of the game. That's part of the adventure. What makes you a good radio technician is figuring all that out.
Figuring it all out. And you know what? That's a wonderful way to describe what those guys in the first EME did. They failed time and time again. What I think is most interesting is they showed up the next day.
Yeah, Lori, there's several people with their hands up. Maybe we should allow them to speak.
Okay.
I think I'll call people in order. You should be able to unmute yourselves. Ovid, your hand is up.
Okay, let's do it. Now, how do I begin?
I just unmuted myself, Lori.
Yeah,
Great.
So go ahead.
This is Ovid, Pomerleau, Kilo 8 Echo Victor. I don't know are you still doing the moon bounce now?
Yes.
Well, the reason that I mentioned 3 DITs, for everybody who likes history, Marconi's attempt from Poldhu in Cornwall was sending 3 DITs, which were sort of maybe, we think, heard in Newfoundland. That was the first transatlantic signal. My effort is going to be more modest. I'm simply going to say CQ DX from Kilo 8 Echo Victor. That's it for me.
We we're playing with this. We found that the moon bounce works fine, however, not over Zoom. So I think we're just going to have to not do that. But lots of people have their hands up, so let's go through those. Cecilia McAfee, you should be able to go ahead, Cecilia.
Hey, Cecilia McAfee Taylor from Tucson, Arizona.
Hi.
Hello.
Hello.
All right. Well, thanks for checking in. We're having trouble sending people's voices out or actually getting them back, but we really appreciate that you checked in. Next person on the list is Scarlett.
Scarlett.
My name is Scarlett.
Hey there, Scarlett.
Anaswan.
Manasquan. Okay, well, that's close.
So happy to see you here.
Yeah. And then Carter Dyke is up.
Hi there. This is a message from KE8.
Hey, Lynn.
What's your call there, Carter?
KE8MTX.
Oh, well, welcome.
Thank you.
All right. And again, for those who tuned in recently, the moon bounce over Zoom is not working as we had hoped, but we really want to, if you can make it in person to the InfoAge site, that would be great once we get past this horrible pandemic. Carolyn Searway is up.
Lynn, is that you? Lynn, go ahead, unmute yourself.
Okay, this is Carolyn McAfee Curry from Mukilteo, Washington.
Hi.
Happy to see everyone
Yeah.
on this historic occasion.
Yeah. Is that Washington, D.C. or Washington State?
Washington State.
Oh, wow. Okay. Very
Mukilteo,
good.
Washington.
Thanks
North of
for
Seattle.
checking in.
Thanks for being here.
And
hi, it's Lynn from Keyport, New Jersey. Thank you, Lori, and everyone for doing this.
thank you for checking
Lynn,
in.
come next Wednesday. We can send the usual message.
Thank you.
And Alan is there.
Hi. I'm Joan Malcolm, and this is a shout out to my dad.
Okay, your audio is not very loud. I think, can you speak closer to your microphone?
Well, we are now into the next presentation.
Okay.
I'm very happy to be able to welcome Cindy Pomerleau to speak about her father and what it's like to be the daughter of someone doing groundbreaking work that would change everything. So please, everyone, mute yourselves at this moment time, and I'm going to go ahead and turn the floor over to Cindy.
Cindy? Okay.
Can you hear me?
Yeah, Cindy and everybody, please just stand by a minute. I am going to mute everybody. And then Cindy, you see your unmute button. So once I've done that, then unmute yourself and we'll start. So here we go.
Not muted now.
Okay, Cindy, so you can unmute and then start.
Okay, well.
Go ahead.
For this tumultuous introduction, and thank you for inviting me to talk about my new book. It's an honor to be here along with the real experts on Project Diana. So for the sake of anyone I've dragooned into attending my talk who might not know about Project Diana, here's the Cliff Notes version. During World War II, my father worked as a civilian employee of the Army Signal Corps doing research on radar at Camp Evans near Neptune, New Jersey, which is why I was born there and where I lived until I was 13. Can you hear me okay?
Yes.
Yeah, okay. At the end of the war, the staffing was being sharply reduced, and many of the military employees were about to be decommissioned. At that point, the director of Camp Evans, not seeing much here, Lieutenant Colonel John DeWitt, with just a few months left to go, was tasked with determining whether Russian ICBMs venturing into the ionosphere could be detected with radar, which many believed was impossible. And since he didn't have any Russian missiles to practice on, he decided to aim his radar at something that decidedly was there, namely the moon. This was, in fact, a long-time dream of his, a feat, as we've heard already, he'd attempted earlier without success. And he knew a second chance when he saw one. So with a very small team of men, and yes, they were all men, and a limited budget, DeWitt set to work. And on January 10th, 1946, they succeeded. At that time, this was a very big deal, making headlines all over the world and newsreels in movie theaters. It was the birth of radar astronomy, the first extraterrestrial communication, and it was also the start of the Cold War. And this is what we're all here to do, celebrate the 75th anniversary of this event. And with that, I'm going to go ahead and try to start my slideshow here. Let's see. Okay. And
Cindy,
Do you have slides, Cindy?
yes, I do. Can you see them?
No.
Wait,
you're not.
really, I can see them on my screen, but let me.
Yeah, so you need to go to share screen. There it is.
Okay, and now I have to get into slideshow, right from start. There.
There you go. You're good.
Okay. Okay, so this is my dad. It's around the time he worked for Project Diana. He was the chief scientist on the team, but as I said, the overall head of the project and the director of Camp Evans at that time was Jack DeWitt. My father was always very clear that DeWitt was no figurehead leader. He was a skilled engineer who had learned a lot from his earlier attempt at a moon bounce. So Jack was very much a hands-on part of the project from start to finish. My father was the head of something called the Special Development Section at Camp Evans, and the remaining group of engineers drawn from that pool were Herbert Kaufman, Jack Moffinson, and Harold Webb. Stadler, Kaufman, and Moffinson were classified as radio engineers. Webb was classified as a physicist, and he was the only one with a doctoral degree. These were the men who did the day-to-day work of designing, assembling, and testing the equipment, the transmitter, receiver, antenna, etc., needed to carry out the project. Other units of Camp Evans were drawn into the project to varying degrees over the course of the project to provide expert input or technical assistance at various times along the way. The most notable by far would be the mathematical analysis section headed by Walter McAfee. I don't know when he started working with the engineering team. It was probably early on, but certainly during the actual moon bounce phase, he was involved on a daily basis because, as you heard, these calculations had to be redone specific to the position of the Earth and the Moon on that at a given point in time. So you'll be hearing more about him later. So, including from one of my fellow Project Diana legacies. Some other contributors were less successful. The antenna design section, for example, submitted a design that was very clever, but unfortunately couldn't be made to work. So the Project Diana engineers were thrown back on their own resources and had to come up with a design themselves, resulting in the famous bed spring antenna, made up of as you've heard, of two SCR-271 antennas cobbled together. And my dad, by the way, always regarded the SCR-270 and 271 as very reliable radars that often worked well when newer, fancier models didn't. So you could see the bed spring antenna. You've seen it several times before if you've been with us all morning, here on the cover of my book. This is, of course, not the antenna we've been using today, but the iconic bed spring, which will surely be on the Project Diana stamp if one is ever issued. That was the dream of the late David Moffinson, has long since disappeared into the dustbin of history. Having mentioned David, a word or two about me and my fellow Project Diana legacies. All our fathers were very young. My father was 31 at the time with the moon bounce, and Herbert Kaufman, Jack Moffinson, and Walter McAfee were all just about the same age. That was a vintage year, I guess. Harold Webb was 3 or 4 years older, and Jack DeWitt was barely 40. So a few of their children may recall the event itself, but most of us probably have only fleeting memories, if any. I was just short of 3 years old. Whoops. These pictures are from around that time. My little sister Leslie was about to turn 1, and my other 2 siblings, Sherry and Bob, had not yet been born. So, and this is it for your dose of baby cuteness, I promise. Having mentioned David, he was my first playmate and sadly now lost from our numbers. But he actually did remember some of the hullabaloo surrounding the event. But a magazine devoted to eyewitness accounts of historical events turned down his submission on the grounds that a 3-year-old couldn't possibly remember something like that. I believe in 100% because while I don't remember Project Diana, I do remember other things from that era of my life. And he and I were the same age. He was 2 weeks before I was. But whether we remember the event or not, most of our childhoods were steeped in Project Diana lore, and most of us have inherited documents, papers, books, and various other souvenirs. And all of us remember our fathers. I'm currently trying to reach out to the remaining legacies so we could pool our memories and share our own special perspectives. And it sounds like Lori's doing that too, so maybe we can sort of combine forces. So back to my journey in writing this book. Okay, sometime in the late 1990s, a friend who knew my father had been a radar scientist told me about a review she'd read in her husband's MIT alumni magazine, a book by Robert Boudry called The Invention That Changed the World, How a Small Group of Radar Pioneers Won the Second World War and Launched a Technological Revolution. It sounded like the perfect way for me to learn more about Project Diana, so I hurried right out and bought the book. Unfortunately, the small group of radar engineers in his subtitle turned out to be the MIT Rad Lab, not Project Diana. In fact, Project Diana takes up just about a little over 3 pages in his book. And the only reason it's mentioned at all is the inconvenient truth that they managed to do something that the Rad Lab perhaps should have done, but didn't, namely shoot the moon and succeed. Boudry provided endless amusement to my siblings and me by referring to our dad as the diminutive bespectacled Ian Stadler. Now, my father wasn't a big man, but we had never thought of him as particularly diminutive, and neither did anyone else to my knowledge. Only later did I figure out how he must have come up with this description. Well, here's the photo of the 5 engineers that you've seen before and was widely publicized at the time, with my father to the right of DeWitt in the photo. He's the shortest one, but hey, someone has to be the shortest. So nevertheless, I got in touch with Bob Boudry, and although Project Diana was pretty much tangential to the research he'd done for the book, he was very kind and helpful. And he did me the inestimable favor of connecting me with the amazing friend Carl, whom you're going to hear from later, and the then fledgling InfoAge, without which I'd probably never have written this book or done any of the things that led up to it. To explain what came next, I have to tell you that my father always felt that Project Diana never received the recognition it deserved. At every milestone year, 35th, 40th, etc., he tried to drum up interest in a public celebration, and he would sort of succeed, but on a local level. And here's a couple of examples. From the 35th anniversary in the Asbury Park Press, he and Walter McAfee are reminiscing about Project Diana. And the other one is from the 40th anniversary. He was living in Florida at the time. And that one, so that article appeared in his local newspaper there. But overall, the Army only provided lukewarm support, and my father never succeeded in inspiring the gala celebration he had in mind. Was it because Jack DeWitt didn't quite get around to asking permission to fulfill his assigned task of detecting Russian ICBMs by shooting the moon? That never seemed quite like an adequate explanation for the Army grey-out of Project Diana, and I actually found it quite puzzling until, with a little hint from a reader, I think I actually, to my satisfaction, resolve that mystery, and you can read about it in my book, but here's the proof. Later, when he worked at the Pentagon, my dad was denied access to his own work on Project Diana because his level of security clearance wasn't high enough at that time. So here's a picture of my dad and stepmother around the time of the 40th anniversary, and as you'll see, not quite so diminutive anymore. So fast forward to somewhere early in the 2010s, when I decided to try to bring my father and his colleagues some of the recognition he'd hoped for by creating a Project Diana website. As far as I know, it's still the only website devoted exclusively to Project Diana, and it needs a little updating at the moment, which I hope to get to shortly now that I've got the book more or less out. Then on January 10th, 2016, which would be the 70th anniversary and of the moon bounce, and 5 years ago today, I added a blog to the website. And that quickly turned into the tail that wagged the dog because it turned out to be so darn much fun to do. I managed to thread my way through a lot of fairly challenging topics, including the bed spring antenna, Armstrong's work during World War II with a little extra help from Ray Chase and Al Klase, and Operation Moonbounce, in which, drawing on lessons from Project Diana, the moon was used by the military as a communication satellite for many years until they started shooting up artificial satellites. I also learned quite a lot about the second moonshot, Apollo 11, when I asked myself the question, what, if anything, had been learned about the moon itself from Project Diana? I also learned quite a bit about my father's work on the development of techniques to detect kamikaze flights, which are in fact probably what he'd be best remembered for if Project Diana had never happened. He later wrote that this earlier work on moving target detection had prepared him well for Project Diana, where their task was to detect a very large and very distant moving target. It also foreshadowed the approach that he used with Project Diana, as I like to put it, work rapidly, using materials already on hand, modify as needed, and then test, test, test. He did a lot of the simulation for the Kamikaze project in a mountainous region in upstate New York near the town of Ellenville, which apparently had just the right configuration for testing methods to distinguish low-flying aircraft from the background clutter and thus eliminate the radar blind spot that the Japanese had learned to exploit. I wasn't even born at the time, but I do remember his taking quite a few trips to Ellenville later, so I guess it continued to be an informative test site. But I knew from the beginning that I wouldn't be able to write essay after essay on technical subjects without quickly getting out of my wheelhouse. I also thought it would be interesting to explore Project Diana's historical, sociological, political, and scientific context, as seen from the perspective of the tiny coastal town, where fate in the form of Camp Evans deposited my father and their neighbors. So I interspersed my essays described above with essays about my father's family background, some of it gleaned from an oral history that I did with him in 1979. My only organizational principle was to vary my subject matter between essays, something for everyone. So here's a photo of my father, with his two younger brothers, and their dog, Sandy. And I also did quite a few posts on my Jersey Shore childhood. Here's a photo I used in an essay called Growing Up in an Amusement Park, and that's me on the right, and three of my friends, with a merry-go-round that was beautiful and no longer exists. My mother made several well-deserved appearances in my blog. My file name for this particular JPEG file is Elsa and King Happy Couple, because they really had an unusually harmonious marriage. Unfortunately, she died at the age of 52 when I had only recently graduated from college, and there were 2 minor children still living at home. Our family had truly lost its brother. So here's a picture I used in an essay about our friends, the Evers family's cars. They're convertible with a rumble seat, and this one, the Willys Jeep. Those lucky ducks had all the good cars. This slide shows some of my childhood activities. Archie, my beloved pet parakeet, was a Christmas gift obtained at the local Woolworths during a parakeet craze. I fully expected him to learn to talk, but his cage was kept right over the telephone, and the only phrase he ever succeeded in learning to say was Asbury Part 2, which was the telephone exchange that he started out with after the operator said number, please. So he heard that often enough to learn. The middle one is my Tony doll, which I still have, along with a lot of the clothes my mother made for her, including this jaunty little jumpsuit. Tony's hair could actually be home permed, so this is an early example of advertising to moms through their children. And the third, playing my ukulele, another Christmas gift, and another 1950s craze that seems to keep bubbling up again and again over every few decades. That actually turned out to be a fascinating story in which Arthur Godfrey, for those of you old enough to remember the old redhead, plays a starring role. I also delved into the fascinating history of the village we lived in, Sharkover Hills, a resort of largely second homes that the Army, by adding a few macadam roads, turned into a sleeper community for Camp Evans, close enough to be reached by car or even by bicycle. This is the Cracker Barrel, Sharkover Hills' only year-round store, looking pretty much as I remember it. It's now larger and more upscale and part of a chain, which I don't think it was at the time. But it's still in the very same place where I rode my bike when I had a few extra pennies in my pocket to spend on a candy bar. This is the old Marconi Hotel, as you can see it today, but it was the first major building on the Camp Evans site, built by Marconi for his workers when he chose the site as being perfect or well suited, at least to his efforts to achieve transatlantic radio communication. I took an interesting walk down memory lane in 2017 when my father was inducted into the InfoAge Wall of Fame, and I realized that as a child, I'd never been inside this or any other Camp Evans building, ever. I clearly remember waiting with my mom and sister in the car for my father to come out. I guess I thought my father didn't go in to fetch him because she didn't want to leave her 2 little girls alone in the car. Only later did I realize that their work was considered top secret by the Army, and she wouldn't have been welcome inside either. So this is one of my favorite Camp Evans pictures and Camp Evans topics. These are Dymaxion Deployment Units, or DDUs, designed by Richard Buckminster Fuller long before he became orders of magnitude more famous for the geodesic dome. They were originally intended as prefabricated bomb-proof shelters, but they were also intended for storage, small workshops, and even vacation cottages, prompting headlines like "A Shelter in War, a Beach House in Peacetime." The Army ordered 100 or so for the Camp Evans site, I think only some of which were delivered, and of which fewer than a dozen remain. They looked pretty shabby when we were there in 2017, but I'm told that InfoAge is now busy restoring the outsides and refurbishing one, both inside and out. As Project Diana's 75th anniversary approached, I started thinking about what I might do to observe this milestone. I already knew that the postage stamp option was out because postage stamps can only commemorate anniversaries ending in 0, so David Moffinson's dream was out of the question. But by this time, I'd written about 4 dozen essays on my blog, and I thought this might be the right time to try to pull them together into a book. What better did I have to do at a time when I was staying at home 24/7? And what could be easier, I thought, than to rearrange them by topic and plug in a few photos? Well, this is the arrangement I finally ended up with, but it turned out not to be easy at all for 3 reasons. First, because when I arranged them by topic, I found that there was a certain amount of repetition that no one would ever notice reading the essays a couple of years apart, but became painfully apparent when they were presented cheek by jowl. That involved a fair amount of editing and what writers refer to as the painful process of killing your darlings. That is, jettisoning whole paragraphs or more of your laboriously crafted prose. I probably didn't catch them all, but presumably I'll do better by the second edition. Second, once I dove into the task, I decided that many, if not most of the essays needed updating, in some instances major reworking. For some essays, I sought additional expert readers, and that too could require adding new information. Third, of the many topics I hadn't yet gotten to, there were a few that I really, really wanted to address. So I had either to incorporate them into already existing essays or to write something new. Then, at the last minute, Diane Webb, another of my legacies, and those of you who were this morning already saw this, sent me this comic book feature from Picture News Comics in 1946, right after the moon bounce, which I knew I had to write up as Harold Webb's superhero, with a little background on the history of comic books. As you see, the title promises nothing short of a round trip to Mars, which I sort of assumed came from the writer of the book, not directly from Harold Webb. I'm not sure about that. So I'm telling you all this about my problems just because I wanted you to know I'm not trying to get you to buy a book that you can read for free on the internet. I think even my most avid followers will find it's quite a different and more comprehensive reading experience. So there was only one possible name for this book, of course, To the Moon and Back, which I have to say describes my book much more precisely than it does most of the other books with similar titles. It's sort of sui generis, but to the extent that it's anything, it's a book of essays, as the subtitle indicates, not a continuous narrative. And the ebook is now available on Amazon in the Kindle store, and the paperback should be out by the end of the month. And I welcome any notification of any errors in either grammar or spelling or in content, and please let me know because I'm always happy to make changes. And if you like the book, please consider leaving a review on Amazon. So that's about it. I'm going to stop sharing, and if there's anything else anybody wants to ask, stop sharing. I don't know if I need to do anything else to send the hostly duties back to Lori.
Yeah. Yes, you're good, Cindy. Thank you.
Okay. I'm done.
So, yeah.
Okay.
So if there are questions, I think please people just go ahead and call them out.
Okay.
Unmute yourself, of course.
Yeah, that would help.
Hi, Cindy. Did any of these scientists later pursue moon bounce in a hobbyist sense with amateur radio?
You know, not that I know of. I'm not even sure all of them were amateur radio.
Mm-hmm.
I know that at least three, Jack DeWitt probably was. My father was, I think Jack Moffinson was, and Herb Kaufman. I can't remember exactly who. I'm not sure about Harold Webb, if Diane is still around. think she said she was not going to be here at this time. I saw her earlier this morning.
Very
Yeah, they
interesting
were
present.
all- and all right, what they did go on to do is Harold McAfee stayed at Camp Evans for the rest of his career. And I think he was involved in whether, you'll hear more about him later. The 4 civilians, my father, Kaufman, Webb, and, well, 3 civilians, my father, Kaufman, and Moffinson, all went to private industry because at that time the Army was sort of jobbing out the research that they'd all been involved in, and suddenly their jobs were, in their minds, becoming less interesting to them. They wanted to continue to do research. Harold Webb was an academic and he went on to become a professor. He went on to study a lot of the issues that came up, but I don't think any of them was involved in the EME to my knowledge.
Yeah, yeah. Just a fascinating presentation. I want to check out the book, and I wish you best of luck with it.
Oh, thanks.
I need that antenna, by the way. I'm only kidding.
The antenna?
Yeah, I need that bed spring antenna. That thing would really get it.
I actually tried to figure out what had happened to it. Obviously got taken down, and at some point, either the Army destroyed it or it got broken down for parts, or it's on it. I have no idea where it is, but as somebody at InfoH once told me, it's no longer available.
Oh no! Oh well. Well, stay safe and thanks.
Lots of pictures. Thank you.
Let me shed some light on what has happened to that antenna.
Oh, yeah.
We often have local people who grew up in this area and as little children saw that antenna come down. And there are parts of the antenna on the hill toward the Shark River still today. Yeah, and that's exactly right, Cindy. It was taken down. Parts of it were maybe repurposed and other parts were just, abandoned as scrap metal. We didn't have the same sense of preserving that kind of history or history in the way that we do today. So if you want a piece of the antenna, you can excavate the land behind ISEC, I suppose, along the Shark River. You might find a
Maybe you can sell little bits of it, like the Wall or the various other
something like that. But yeah, the antenna was definitely taken apart, and there, from what I've been told, kids used to play with the excess parts. Yeah.
Yeah, I'll make one comment on that. The SCR 271 tower at Alpine still stands, but it has a different antenna on top of it now.
Well, one of the things that we do have are the posts and a concrete pad where the antenna stood. So today we can go there. There's a picnic table on that concrete pad at the moment, but it is still there. The pad that the antenna was on is still here at the Diane site.
For information on antenna, for you people who want to collect antennas, there is an SCR 270 antenna on display at the National Electronics Museum in Linthicum, Maryland. That's right near the BWA airport. National Electronics Museum is a great museum, and they have one of the original modified SCR 270 antennas. Also, before Fort Monmouth closed, Al Klase and I were privileged to visit the storage area for their museum, and they had a complete original SCR 270 antenna on a trailer in their storage area, and we are trying to track that down, but I'm sure in some warehouse someplace, which may never be seen by.
Yeah, some warehouse someplace right next to the Ark of the Covenant. So I'm afraid it's gone.
But yeah, we lament that the everything that was used on the original moon bounce experiment has been scrapped. No one thought to keep anything. So that's history for you.
Hey, Ray, that the Linthicum Museum there is fantastic. I did get to see that SCR, took a zillion photos. And there, if you go inside, well, first of all, there's a ham shack. So if you want to operate, if they're open. But there's also a great display about Hawaii and how they were testing out the SCRs in Hawaii. And the guys didn't really know, much about it yet. And they said, wow, we've detected some weird signals. Well, it was the planes coming in, bombing, Hawaii. So it's a great display and a fantastic exhibit there. So if you're going to be down in the Linthicum area, plan to spend a couple of hours in that museum. It's really fantastic when it's open.
Thank you. I have if anybody's interested, I have a PowerPoint display on the history of the Pearl Harbor radar and what really happened and didn't happen. So I've researched that quite heavily. So if anybody's interested in that, I can put that on at the Radio Technology Museum at InfoAge.
Any other questions?
Yes, I have a question.
Yes.
Do you hear me?
Yes.
Regarding the collection of historical artifacts or antennas and radio, I've been on a mission now to recover some of the panels of the Arecibo dish that was destroyed. It's got like 38,000 6-foot by 3-foot precision, well, those that were not torn up, precision aluminum surface panels.
Wow.
And my idea, I haven't gotten permission yet, but my idea is to get some if they're available, and then make them, if you think about it, make them as presentation backgrounds to the Moon Bouncer of the Year award or a Nobel Prize award, something or another. The award could be put up on, they're 3-foot by 6-foot roughly, perforated aluminum screen. And so they could be award backgrounds, and a professor somewhere could hang it in his office somewhere at Princeton or wherever and say, that's an Arecibo reflector panel that we saw. But I don't know, how would I say this? I don't know the right person. Sorry?
Give us one at ISEC. We would love it.
I'm sure there'll be big demand, and there might already be somebody that's sort of trying to figure out how to do this. But if anybody knows anybody at Arecibo that can make decisions or be sympathetic to such a thing. The other thing is, there's so many of them that in Moonbounce, we've done some other things for kids. And I'm thinking if somebody says, yeah, can you make 20,000 of these disappear from the site and take them away somehow? I don't know if it'll come to that. But if that happens, each one could be used as an easel for space painting or space themed artwork. And that was the other idea I had, because the perforations are like very small, but it's 3-foot by 6-foot. And if somebody has taught astronomy in middle school, let's say, they could put one up over the blackboard and say, this is from Arecibo salvage. So I'm trying to get that, I'm trying to figure out how to get a line on that. And they're aluminum, not very heavy, kind of big, 3-foot by 6-foot. But that's my mission since Arecibo has fallen down. Anybody wants to join or have ideas on how to grease the skids or get to the right person to dispose of those, maybe for their scrap metal value or something.
Well,
anyway, that's
well,
He's
I have visited Arecibo several times. I've been there 4 times. And I can tell you that that may be possible. Just the way that the place was run and how accessible it was to people who were doing real research. I think that, maybe we can work together on that. Email me and maybe we can make something happen.
What's your email?
So it's LoriLauber@gmail.com. And I sent it out to everyone in the chat. I think, in fact, I
Okay.
sent it to you and you responded.
Pat,
Oh, okay. Sounds good. Somebody else calling? Say again.
this is Al. Hi, Pat.
Oh, hey, Al.
KP4WG Angel. If you look in the
Yeah, Angel Vasquez, right?
Yes, he would be your best bet.
Okay,
He worked there.
good.
He's got good contacts. Okay.
Right. Thank you very much. I'll get in touch with him. I was there, by the way. I operated Moonbounce from Arecibo some years ago.
Yeah,
and so I know.
I
Sorry.
was just saying you're documented in the write-up that appeared last newsletter, if you look carefully.
Oh, really? Okay, I'll take a look. All right. So anyway, but you can imagine if they got 38,000 of these things, you say, could we have a couple of hundred?
Yeah.
And they might say yes. And then you could paint them or artistry or make them a special award background, a hanger for some professor or somebody that did something on Project Diana or something like that. They're quite. In fact, I published a photograph of one of the panels. Unless you know what they were, they just look like a piece of aluminum that's precision formed and has little perforations in it. But it's the Arecibo panel. Okay.
Okay, any last questions? I'm about to introduce Fred Carl, without which we would not be here today. It was Fred Carl whose greatest efforts were to save Camp Evans and particularly the Diana site. The Diana site was called the Tyros site for a while when the TLM-18 would follow the Tyros weather satellites. But there's a little known secret that we tell people when they come to visit. The TLM-18 was also used as part of something called the mini-track system. And the mini-track system was a system to make sure that we were watching their satellites while they were watching us. And this particular dish was part of the calibration for that mini-track system, and it was used regularly. So the public knew it as the Tyros site, but I think of 007 when I think about that era of, the TLM-18 being used. It's been here since 1958, and it truly has been, through so many different changes, and it's done a lot. And today we are looking out as far as the Andromeda Galaxy with it. So if there are no other questions, can I go ahead and introduce Fred Carl and let Fred get started? Yeah. Okay. So Fred is difficult to introduce because of all the great work that he has done to make this place possible. Fred is now doing some very serious work through Princeton University and the Simons Observatory. Let Fred talk a little bit more about what that is. He is doing super work, groundbreaking work, and I guess that it's his time to do that kind of thing because he's already saved Camp Evans. We are a national historic landmark due to his efforts, and we're happy that that has happened because we will be here in the future. And Fred, can you go ahead and take it away?
Thank you, Lori. It is truly a thrill to be here. I'm trying to find the proper screen to share. And thank you for that nice introduction. Let's see. Oh, good. All righty. Let me see. I'm having a little trouble going to slideshow mode. So can you see my screen?
Yes.
Okay. I have an auxiliary screen, and when I go to slideshow mode, it shows up there. So I'll just work from here if that's okay. The challenge. Radar astronomy is a technique of generating energy and bouncing them off large targets. The challenge is that nasty inverse square law. So that's the main problem. And if those of you remember Tim the Tool Man, more power, that's been the history of radar astronomy, getting more power. This is what I find amazing at this site. It was first put together on the thought that you could use the luminous ether to move radio waves across the Atlantic, where later they would find out, thanks to Oliver Heaviside, that there was a layer in the atmosphere called the ionosphere, and that was actually bouncing the radio waves across the ocean from Wales to what we now call Camp Evans. So it is really amazing that a site that depended on the Heaviside layer going all the way back to Marconi is the one that actually demonstrated that you could pierce the ionosphere and bore the birthplace of a new branch of astronomy called radar astronomy. Fantastic. And, the old joke, wait, there's more. Well, later they used the site for ionosphere research, moon surface study. The TLM-18 would start Earth observation, regular Earth observation by satellites, which changed so many sciences by feeding them tons of data, daily weather images, the birth of satellite tracking, and as Lori alluded to, spying on the Soviets. Wow. And now it's a historic site and it's a working educational site. Thanks to Dan and the team from Princeton, it is beyond the dream. Its first use as a radar astronomy site after bouncing off the moon is alluded to in Dr. Zoll's Electrons Away book, where a professor from Princeton, John Quincy Stewart, there's his photo next to Dr. Zoll, they attempted to track drachnids, and they were more or less successful. But it was tough because it comes back to the power, right? Now, to get the power, you needed military equipment. And sort of like the history of radar astronomy is tied to getting military support. So Diana was a reused SCR-271D. The Lincoln Laboratory with their work at bouncing radar signals off of Venus, another leftover military device. Arecibo, as most of us know, is no longer operational, and it's sad, but that was sort of like the apex of radar astronomy. And again, it comes down to you need a place to either transmit the signals, bounce them off your object, and receive them back. In the case of Arecibo, it could do both. Here's an asteroid that was characterized by radar astronomy, because now, like all astronomy, you just don't need equipment, you need computers to put your images together and take out clutter, right? So I've been very lucky, and it is so much fun to be part of the current work in learning more about the cosmic microwave background, which started in Homedale, New Jersey, with some lucky Nobel Prize winners who had a background noise, as many of you know, and it turned out Princeton was looking for that noise, and they were scooped. Whoops. So here is Dr. Brian Keating, one of the gentlemen I work with. In a Zoom meeting, he complained that his whole career was with cosmic microwave background study, and he had never been to Homedale. So I said, Brian, next time you're in New York City, I will drive into the city, and I hate driving in the city. Pick you up, take you to Homedale, take pictures of you in front of the dish for your next book. And that happened. And I brought him back to Newark Airport. It was fun. But this is what him and his underwriter and his team are doing. They are making the best to date set of telescopes to learn more about the cosmic microwave background by getting more, I guess you could compare it to a bigger pixel set of cameras, okay? And because they want to answer the big question, right? What is out there, right? And this has been a perplexing thing for mankind because our first telescope was our eyeballs. Then Kepler came up with the first artificial aid, the telescope. And we kept going through these demotions where we were the center of the universe and God and all the angels were around us, making sure we were okay. Well, the sun's in the middle and now we're the third rock from the sun. And whoa, wait a minute. Our little planetary thing is just one star among the Milky Way in a galaxy, and we're spinning. And wait a minute, those stars out there, they're not stars, they're other galaxies. And then, whoa, it's expanding. So with better and better tools, we learned more and more and found more things. So part of the advance in astronomy is not just the brilliant people who come up with the theories. It is the tool makers who enable more information to come in, right? So the Big Bang was theorized, okay? How you like this view? The idea was 380,000 years after the start of the Big Bang, you had photons given off. And after all this time, you should be able to find those photons. And again, it was done in Homedale, New Jersey. Here's another view of the Big Bang. And the hope is by finding more data, you can predict where galaxies will be formed or galaxy clusters, okay? So what is the cosmic microwave background? When it started, or the expansion of whatever was out there, the big kernel, you had sort of a primordial soup, and there was so much energy, you couldn't have electrons get in orbit around a nucleus. So eventually, as it expanded and cooled, you had this time called the recombination, where the photons came off, and that's what we're looking for. And again, it's been a progress in resolution. Here's our Homedale horn. That's our 1 pixel camera. And then a satellite was created that could find the microwave background and look at a better resolution. They found there was relative hot and cold spots. And then here's WMAP, named after Wilkinson, right? Notice you have a better resolution. Well, now here's the team working thanks to the gifts of the Simons Foundation. This team of amazing PhDs and leaders in their field are leading this team of 200 scientists and staff to create the next tool to find more about the cosmic microwave background. This is us at Berkeley. Each year, the team has a team meeting, and because of this pesky pandemic, the team was going to meet in Princeton, and we were arranging tours for those interested to come to InfoAge. And not the only thing that got canceled. So here's the team I work with directly in Princeton, and they are just amazing. I've been with some of these students when they were just new graduate students. And one of the joys of being part of this team is Dr. Staggs, watching her give the students more responsibility. And I've watched them grow from timid little graduate students or postdocs to real confident young scientists. It is really neat. And it is a gift, and I am so thankful for it. So our challenge is to get us light. But the problem is we just don't want any light. We want the cosmic microwave background. So we have a lot of problems. There's clouds out there. There's dust. We got to concentrate the light with lenses. You can only see so far at a time. Do you like my pun there? Now, the other problem is too much light from other things like the sun. You can have reflections with light coming in that you don't want. There's issues with physics, and there's instrument effect. So we'll talk about some of these. Here is one of the lenses or devices, a cross section, that goal is to capture photons, have them filtered through filters, okay? Catch things on the side that are reflected, take away unwanted heat generated by the energy of those photons hitting the filters, and then having them picked up by what's akin to our iris at the back, and then sending data to computers to do analysis, right? So it takes advantage of a phenomenon discovered with the drops of mercury called superconductivity. And if you set certain substances at the right temperature and a photon comes in and hits it, it will change resistivity. And using a concept that I believe Ray and Al and company have a Wheatstone bridge at the thing, this tried and true concept put in miniaturization can actually detect a photon hitting in the telescope, okay? And here's a comparison. The Holmdel horn is a 1 pixel device. Look at the size of it, okay? And here is one of the feed horns in one of the arrays that we'll learn more about, okay? So here we're looking at the akin to the iris, okay? And here's where these either lenses are or feed horns that are capturing light coming in, right? And the challenge is to detect the light and then turn it into electrical pulses to go into computers. And it is microelectronics at its key. This is a clean room located at Princeton. And this is one of the postdocs working on doing loop connections. I'll show you more. Because look at the tiny circuits you have here. Behind each lens and behind each cone to focus them on is a tiny circuit that when it hits this bolometer, it sends a pulse down here, and each one of these has a different size and a different wavelength that'll send out a microwave to be captured in its time frame, because they do time division multiplexing. So now these photons are very cold because they've been traveling for billions of years. So they're now in the low energy microwave state. So you need something to cool them down to nearly absolute zero. And they use these amazing pulse tube coolers and to bring things down to near absolute zero. and they're kept in vessels called cryostats, which are like, think of Russian dolls, okay? Well, inside the tiniest doll is the electronics, and each layer protects the inside layer from the heat of the outside environment. Because us here enjoying our, I guess it's like 380 Kelvin, if I don't have that wrong, we're nice and warm. You can't detect the photons that you want with that, okay? So originally the device was called a camera because it is akin to a camera. And here's all the layers of your Russian dolls, okay? Each layer insulates it, and you have to carry out on very thin wires that will not give off too much heat, that could be picked up by the bolometers as photons. You want to get it to computers. Again, you have filters to take out infrared rays and things that you don't want to hit your bolometers. Here again are cross sections of the two different optics tubes. And notice at the back of each one, you have your electronics. So you want to, inside, those of you who are have visited Camp Evans, there was a building, a Quonset hut, that had thousands of these cones that was like an anechoic chamber. Well, inside of these optic tubes, it's sort of like an anechoic chamber. Any photon that comes from a reflection from something that you don't want, or is generated from the filters as heat, you want to capture. And of course, the refrigeration will take that heat away. Now, what's unbelievable to me, it's one of those things that until you see it, you can't believe it. As you know, light waves, if they line up crest to crest, will complement each other and boost the signal. But if they don't line up, they can cancel one another. And so the lenses, they will lose light coming in through reflection off the front surface and the inside surface. So look at here with no AR coating. And notice you have areas where the light is canceling out in the dark areas, and where light is being magnified because of the crests of light waves hitting one, lining up together and complementing one another. So the lenses are in the process, and this is happening right now because these telescopes are being built all over the world. I believe it's in the University of Chicago. They are taking lenses, sapphire lenses, and running tiny blades across them in multiple passes. First pass to get this depth, second pass to get it a little wider, third pass. And believe it or not, when the light waves hit this, more of them go into the lens and further than if it was a completely smooth surface. Okay, again, baffling to capture the stray light. Here is the cryostats. This is the large cryostat, which goes inside here in this giant telescope that is 6 meters across at the opening. And each one of these, there's 2 mirrors that reflect the light into the cryostat. And this cryostat was manufactured and still is at the University of Pennsylvania. And each one of those cryostat is set up to hold 13 optic tubes, of which the experiment will put in the initial 6. And here's the size compared to humans. These are graduate students. Now, the challenge is you get a lot of things coming in because there's a lot of busy stuff out there in the sky. So you need sophisticated computer algorithms to go through and pull out of all the light coming in what's potential microwaves coming from a star, coming from a galaxy, coming from maybe dust, okay? So it is quite the job, and that's part of the leading edge of this experiment, and it's open source work, and there are people all over the world in dozens of universities contributing their expertise to this, these algorithms. So here's what we see out in the Atacama Desert, out in Chile, where it's about 17,000 feet high. And at the beginning of this experiment, when I got involved, people said, would you want to go to Chile? And I was like, yeah, it sounds like fun. But then as I learned more that to walk around the site, you need oxygen. And one of the major components are being built in Italy. Another one is being built in Germany. You know, they both have better beer. They have lots of oxygen, and Italy has gelato. So I put my hat in the ring to go to those sites, but again, we're back to that pesky pandemic. So this is what the telescope sees at 2.7 Kelvin. And with the work of those sophisticated computers, this is what the data analysis shows. And the site, the Simons Observatory, this is where the new telescopes will go. The telescopes are the design of the telescopes are being used by other projects. So this is not just a one-off. This may serve cosmology for the next 50 or more years because you'll be able to put in new optic tubes with the latest cryogenic knowledge or the newest materials and techniques. So it's really thrilling. And I want to go back and highlight Dr. Jim Simons, who is retiring from his foundation, the Simons Foundation, who doing analysis and algorithms of why people buy stocks as a professor, a mathematics professor in Columbia, formed a limited liability company that I'm told is a legend in the industry, Renaissance Corporation. And when he had had enough fun, he had $18 billion in his back pocket. And so he's formed this foundation with 85% of his fortune, and he's kept 15% for himself and his family. And as he puts it, that's more money than he could ever use. So he is a great philanthropist. And another one is Dr. Keating had invited him to come and visit InfoAge. And of course, that pesky pandemic again. But we're marching forward in spite of it, even though the grad students and the postdocs are limited in the time and the number of people that they can get in their laboratory at once, the project is moving on and making forward, and we project that we've only lost 5.4 months in this endeavor. So thank you. And any questions?
Fred, are you in the picture?
There's my smiling little face. It was really fun. It was a great couple of days to be in Berkeley. And here's Dr. Keating. Oh boy, Devlin from University of Pennsylvania, the new head, David Sergel of the Simons Foundation, because Jim Simons is retiring. It's really fun. Like I kid people, I am a science person, like a baseball fan, and I'm getting to work with the Yankees. And it's the thrill of my lifetime. And there's times where I think, what was the bigger thrill, Camp Evans or Simons Observatory? It's a blessing to have such a problem. You can't figure out what's the best thrill in your life. So that's it.
Hello, are you still there?
Yeah.
This is Pat. I had to leave, but I came back and got the latter part of your presentation, especially that involving the super dark absorbent baffles that remove extraneous light. It turns out that I just read like 3 days ago an article about use of carbon nanotubes, which are a whole new technology. They found a use that looks very much like that for structures made out of carbon nanotubes that are awesomely blacker than black and extremely low reflectivity. I don't know if you're interested in that, but it was a feature article in one of the technology magazines.
Okay, was it based on the work of Dr. Akito Kusaka of the University of Tokyo?
Yeah, that sounds about right. I'd have to look at it again, but I have the magazine somewhere else right now. But
okay,
it could be. I don't know.
Right, back to living the dream. You know what I mean? I get to talk to that gentleman twice a week, among others.
In a similar way, my hobby of moon bounce has introduced me to some really incredible people, Nobel scientists, and who happen to be moon bouncers, and other people like over at Arecibo. So I know that thrill. Even looking from the sidelines. Yep. All right, so I can connect with you somehow and send you that article if you're interested.
Yeah, it's simple FCARL@princeton.edu.
Excuse me, I have a.
Okay, go ahead.
I have a technical question. These cryogenic telescopes, what wavelength bands do they work in?
Whew. I should know that right off the top of my head, because we refer to them as medium frequency, low frequency, and high frequency, but I can't give you that off the top of my head. It's all different microwave frequencies.
Are these the characteristic frequencies of temperatures around 3 Kelvin?
Yes.
Yeah. Okay, I can calculate it. That's all right. Thanks.
Well, you can go to a website, simonsobservatory.org, I think it is, or just Google Simons Observatory, and there are papers describing the instrument in more detail than I can keep in my head.
Okay, thank you very much. Excellent presentation.
Thanks.
Thank you for the presentation, Fred.
Oh, my pleasure.
This is Charlie Smolin. Are all focal plane arrays bolometers as compared to other kinds of imagers?
Well, there was a lot of discussion early in the project before I got there of using other technologies. One was called MKIDS, and where we're using transition edge sensors. So there are a number of technologies, and that's the one the project landed on. And there are this same telescope design with this same optic tube design. There are proposals into the National Science Foundation to do similar telescopes, but using MKIDS as their detectors.
Okay, thank you.
Well, thank you, Fred, for that incredible presentation. I think that it's important at this point to say, wow, You mean this all started here at the Diana site with a simple moon bounce? Yes, it did. It's an incredible thing that we can talk about the future of space exploration in this way, and that we can relate what happened here with these 5 men in 1946 to the future of the human race as we look out of our local neighborhood and see if we can continue, if we can only just keep it together here on Earth. We have been challenged, obviously, by the pandemic. And I just want to thank everyone who's been involved today, because this was the only solution. Today's event was supposed to be a 2-day event with speakers all over campus. And when we opened back up, because InfoAge was closed for nearly 6 months. When we opened back up and we said, okay, what are we going to do now? I thought, well, hey, a 7-hour Zoom meeting looks like the only answer. And we've all had to learn how to do this. Every one of us who is here is a participant or is a speaker. And I think that we are really, really lucky that we have this medium to be able to still get together and share information. I have been asked to read a statement by one of the daughters of the men on the team. And in fact, it's Harold Webb's daughter, Diana Webb, who was named after after Project Diana. So I want to go ahead and read her statement. And bear with me. If you have questions for Diana, I can feel them, I hope. And if I think she's still here with us, she may be able to answer them. So let me begin. These are remarks prepared by Diana Webb, the daughter of Harold D. Webb of the original Diana Project for the 75th anniversary on January 10th, 2021. Diana says, I appreciate the opportunity to share a few memories of my late father, Dr. Harold D. Webb, on this, the 75th anniversary of the remarkable achievement of Diana Project. Dr. Webb was one of the first 2 people to hear the echo of their radar beam as it bounced back from the moon, and was a major contribution to the success of the project. Diana Webb is his daughter, and she's proudly named after Project Diana. She says, my father was a physicist who had a lifelong interest in radios and astronomy. Following the completion of the Diana Project, he left New Jersey to become a professor of radio astronomy in the electrical engineering department of the University of Illinois, a position that he held until his retirement. Dad was a quiet man and humble. He grew up on a farm in central Indiana. Even after graduating from college, he continued to do chores and milk the cows every morning before changing from his barn overalls to his suit, then headed into town to teach at the local college. He married my mother, Margaret, in 1937, and soon after received his PhD in physics from Indiana University. He continued to teach physics and math until he was recruited to join the Army Signal Corps in the early 40s and joined the Diana Project team at Camp Evans as a civilian scientist. Growing up on the farm, Dad had lots of time to observe things around him. He read about the radio pioneer Marconi and built his own radio out in the barn. He would skip stones across the little pond in the back 40 near the railroad track and listen to the train whistles as the long freight trains passed by the farm. Later, he would tell me, these experiences came to mind when he was working on the Diana Project and helped them turn the project from potential failure to an astounding success. Why? Well, Dad explained it to me this way. Dad felt that 2 of his most significant contributions to the Diana Project were his idea that the shot would be conducted at moonrise and his calculations regarding the Doppler effect on the radar beam. Dad realized, like the train whistle changing its musical tone as it passed the farm, any attempt to bounce a radio beam off of an object as far away as the moon would have to take into account the fact that the beam would change frequencies as it traveled all the way to the moon, hit it, and traveled all the way back. This change in frequency over time, called the Doppler effect, is why a train whistle appears to change in pitch as it gets farther away. The Doppler effect had to be taken into account and precisely calculated for the Diana project, or else the men sitting at the radio receiver would not know what frequency to tune their apparatus in order to receive the echo, if they were to hear it at all. Simple physics, Dad would say with a grin. Dad also made a major contribution by determining which way to point their large, awkward box spring antenna, the big square antenna that is now the visual icon for the Diana project. He told me that at first they were trying to point the antenna at the moon when it was overhead, but they were not having any success in getting their radio beam to penetrate the outer limits of the Earth's atmosphere and come back to Earth. Some people told me, poo-poo. He had been poo-pooed, and the idea that a radio beam could even make it out of the prison of the Earth's atmosphere. But he remembered, as a boy, how he had skipped stones across the pond at the farm and suggested that they try contacting the moon at moonrise, just when the moon came up over the Atlantic Ocean. That way, he explained to me, they could skip the beam at a low angle and take advantage of the greater antenna gain over the surface of the ocean to make it past the Earth's ionosphere. Dad's knowledge of how to construct a radio also came in handy as he helped fine-tune the equipment allotted to the Diana project. By late 1945, the Diana project was foundering. No success had been made in reaching the moon with their radar beam, and some of the project leaders began to talk of giving up or trying a different type of equipment. But Dad suggested to the project leader, Colonel DeWitt, that they should try the antenna pointed at a lower angle, and DeWitt gave him 1 week to try out his new idea. After they adjusted the antenna, Dad kept his notes of the new attempts in a little pocket secretary notepad with a maroon and white cover designed to slip into the inner pocket of a man's suit jacket. Dad started his notes in his new notepad the morning of January 10th, 1946, the third day of their week-long attempt after adjusting the angle of the antenna. Dad and Mr. Kaufman were the only two in the room with the radio receiver that day. Moon data, the first line on the notepad reads, in Dad's familiar scrawl, moonrise, January 10th, 11:48 is the first entry. Heard echo at 11:48 and 12:09, audible only. Not quite sure what they heard. They wanted visual confirmation of the echo on their oscilloscope, but they didn't see it. The next day, they tried again. Moonrise, January 11th, heard and saw echo at 10 and 20 minutes after moonrise. Now they could see the telltale blip on the screen. Now they knew for sure that they had contacted the moon. Dad described the event like this in a little write-up he prepared shortly after the event. We saw the moon by radar. It was at 11:58 a.m. on January 10th, 1946, just 10 minutes after moonrise. I had been watching the oscilloscope connected to our special radar for some 30 minutes or more and felt somewhat drowsy from the monotony of the clashing relays and the faintly audible noise coming out of the loudspeaker connected across our oscilloscope. Suddenly, Mr. Herbert Kaufman, a co-worker on the project, came running into the room and said excitedly, "Did you hear that?" He then turned up the speaker again, and we both listened to a series of audible notes indicating echoes from the moon pulses of radio frequencies energy that we had aimed in that direction. This was a moment of triumph. For several months, we and other Army officers and engineers had been working on this experiment, but never before had any of us been sure that we had previously received echoes from the moon. We knew that this thing was the real thing. We decided not to tell others about our success yet. We were sure that we had succeeded, but there was some fear that something else could have caused the audible tones, because the notes didn't seem to have the proper pitch, and because the signal was audible only while we expected to see it on the oscilloscope. Mr. Kaufman did tell his supervisor, however, and I told Mr. Moffinson, who was also working on the project. We were ready with enthusiasm at moonrise on January 11th. Mr. Moffinson and 3 other persons were present besides Mr. Kaufman and I. I was working with an adjustment that previously we had not been sure of, just a few minutes after moonrise. Then suddenly we received several quite strong echoes, both audible and visual. It was 10 minutes after moonrise. About 20 minutes after moonrise, we received a series of several more echoes from the moon. Now everyone was present and were sure that this experiment was successful. And so history was made. So what was the life of the Webb household like that January, 75 years ago? Dad was 36 years old, and Mom was a few years younger. They lived in a 2-story farmhouse with a big front porch in Belmar, New Jersey, on 8th Street, near the Shark River. The house is still there. While Dad was busy trying to contact the moon, Mom was busy at home. They had 3 little kids then. My brother Steve, age 7, my sister Pat, about to turn 6, and my sister Sharon, who was about to be 2. I wasn't born yet, Diana says. In a letter that she wrote to her brother that January, Mom spoke of making Patty a new dress, taking all 3 kids to a birthday party for Cynthia and Leslie Stodola. Elsie had lunch and ice cream and cake for all of them. The week of the historic moonshot, all 3 Webb kids had chicken pox. She said, so I've been pretty busy, and she wrote to her parents. She discussed the pox, the weather, the rain and the snow, the kids' Christmas presents, and at the end of the letter, a brief mention that Dad had been out to Camp Evans. They have been working on a small project, she said. It's a special project that may be in the news, maybe one of these days. You might see something about it. That special project, as we know now, was the Diana project, and it was the beginning of the space age. Dad and other men became famous for a while. They had to sign a notarized affidavit that they did, in fact, contact the moon by radar. No fake news here. The Diana project made headlines in all the major newspapers of the day, was written up in magazines, became part of the popular culture of the day, was used to sell Pepsi and other products, and was featured in a newsreel shown at movie theaters across the country. The way that people got to see news back then. This is how national news events in those days, before television, was shared. The newspapers printed front page drawings of Buck Rogers-style spaceships going to the moon, and Dad was even featured in a science-themed comic book. My sister Pat saw it differently. Knowing nothing of the world events, but knowing everything a first grader knows, she remembers asking Dad about Diana Project. Then, almost 6 years old, she knew that Daddy had done something because people kept talking about it. So she asked him what he did. I bounced a radio beam off the moon, she remembers him telling her. Well, why did you do that, Daddy? She asked, sparing her the astronomical details about ascertaining the exact distance of the moon from the Earth. He answered, to find out where it is. Daddy, I know where it is, she said indignantly, thinking that this was a stupid project for a bunch of grown men to be working on. Didn't everybody know where the moon was? Just go outside and look up. The Diana Project became part of our family history. We were steeped in the details, the names, the places, the mythology behind the name. I was born in September of that year, and my parents named me Diana. After the project that had been Dad's focus for all those months, I grew up knowing about the Roman goddess Diana, the goddess of the moon, and all about the moon, my moon, that had brought my dad some degree of fame. I am glad that ISEC and InfoH have rekindled the public interest in this project and that all the people who worked on the Diana project can be rightfully remembered as contributing in a meaningful way to the beginning of space exploration as we know it today. I still feel a strong attachment to the moon, and even today, now that I am almost 75 years old, when I see the full moon, I think of my dad and say to myself, "Hi, moon, Dad touched you first." What a great account of what it must have been like to be a regular, everyday person, getting up in the morning, having breakfast, making your lunch, and showing up at work. A work that was not necessarily fulfilling if everything kept failing. But these guys got up every day, and that's what they did. They kept trying, and they tried again and again. And one of the things that we do here at InfoAge is that we encourage kids to look beyond their everyday failures and to achieve what others may tell them is impossible. And that's what these guys did. So thank you very much, Diana Webb, for sharing that account of your experience. And let me just say to everyone who is here now, and I know that you're not children, but when your failures make you feel like giving up, don't.
Pure gold, pure absolute gold. You should, is there a way that you can present that text somehow here or put it online that we could see that?
I can try. It's an
Lori? Yeah, I'm going to put it on my Project Diana website. So.
Fabulous.
Excellent, excellent,
Yeah,
excellent.
no, Diana's fine with that. And it's actually part of what I'd originally hoped to do was flesh out the men who were involved. And it's hard to find that kind of information.
That's right.
So I think this is a gem. And, you know, I've got, as much as I can, I'm getting material, similar material for each of the people involved. So
thank you.
Hi, this is Diana. Can you hear me?
Diana.
I'm sorry I could not participate. I'm actually out driving. And so I appreciate very much you reading my remarks, Lori, and you did a great job of reading them. And Cindy, thank you for the offer to post my remarks on your webpage.
Yeah, Diana, I will try to share your remarks. Somehow I have to copy and paste the email, but I would love to share your remarks. They were fabulous, and thank you for taking the time and being so candid about everything. And folks, I just want to tell you that I have seen those original notes. One day in 2018, Diana came as a visitor to InfoAge, as many other people do, and she introduced herself. I was honored to meet her. And then she gave me a box full of her father's work. And I have seen that little notepad and have read the notes that that Harold Webb wrote on January 10th and 11th. And it's all true and I think magnificent. So thanks, Diana. And let me see how I can share our comments. We have 10 minutes before we go back into the technical side of this presentation. We've got Charles Cebula, who's about to speak. And one of the things that Charles is able to do is tell us exactly what that math that got us to be able to calculate for the position of the moon from any position on the Earth. Now, that really was difficult to do. We had an idea of the distance between the Earth and the moon, but it wasn't perfect, obviously. And Walter McAfee did some very, very fine calculations that made it possible for us to calculate for that Doppler shift. Today, when, if anyone was here when I did the moon bounce, I just look at my UHD FFT window and I can see the frequency at which I sent the signal. And with a little bit of calculation, minus 0.500 in hertz, I can change the fine tuning on the radio and hit the moon and know that I will hit the moon. He did the work for me. And so does the computer. We do the moon bounce regularly. And it is thanks to the mathematics that got us there. So please let me see if Charlie is here. Charles, are you here?
Yes, I am.
Can you unmute yourself? Good to see you.
I did. I'm on
And-
it. I'm muted. You want me to share screen?
In a moment, I just want to ask one final question. Does anyone else have a question for Diana or for Fred?
Just for Diana, just
Yeah, go
restatement. It's pure gold what she said and what you read. It's got to be
I
preserved.
love it.
Yes,
It
I
is
wanted
preserved.
to say, that was fantastic. I got teary. I loved it.
Yes.
I would also like to share. Can you hear me?
I can hear you.
Yes.
I'm Joan Moffinson.
Hi, Joan.
Hi.
Look for you.
What's that?
Email me.
I wanted to especially thank Cindy for her presentation. I didn't have a chance to say that, and I loved seeing the pictures of my brother and Cindy in the little tub together. And I heard part of the Diana's letter. I wasn't able to hear the whole thing, but it's heartwarming and very, very poignant to listen to all of this. And I also will send something into the website to share about my recollection.
Do you have my email address?
Tell me again, Lori, what is it?
It's Lori, LORI, @gmail.com. And I will share it with everyone again.
Yeah. Okay, great. Terrific.
Thanks for speaking up. I didn't know it was you.
I'm not very technologically inclined, even though it's in my genes, but I was trying to figure out how to do what. So,
well, I'm glad you're here with us. I'm glad you
I'm
joined
better
us.
at writing. But
Yeah,
thank
it's
you
okay.
so much.
Glad to see you. Let me go ahead and continue with the program. So as you can see, this moon bounce is much more than just all of the technical work, but it wouldn't have happened without the technology. And Charles is going to show us what that was. Go ahead, Charlie, it's all yours. And don't
Okay,
forget.
let me share screen here.
Right.
Let's see if I can get my briefing up. It'll take a few seconds here because it's a large document. Do you see it?
Yes.
Okay. Okay, good afternoon. My name is Charlie Cebula, and I welcome the opportunity to provide this brief on Dr. Walter S. McAfee, an important pioneer and hidden figure who played a critical role in the success of Project Diana. I would first like to thank both Diana McAfee and Cindy Cebula for the contributions of their dad to our great nation. I worked at Fort Monmouth for 38 years, and I know lots about Dr. McAfee's contribution to technology in support of our warfighters. I'm also a ham operator, and I know that Mr. Cebula was not only a contributor to Project Diana, but also his support and dedication to ham radio. We heard about E.K. Cebula and Colonel DeWitt, who led the project, but it took the efforts of a savvy physicist and mathematician to perform the required mathematical calculations that made the success of Project Diana possible. And there's a picture of Dr. McAfee who passed away in 1995. Okay, I'm going to go over this little outline. We'll talk a little bit about hidden figures, and we'll talk about that. Dr. McAfee's background education, how he really was a hidden figure. We'll talk about Project Diana radar, which you may have already heard a lot about with the presentation of Mr. Edwin Armstrong's radar, which was used in the project. And then we'll talk specifically about the two contributions to Project Diana, which was the use of the radar equation to prove visibility of bouncing a radar signal off the moon, and the use of Doppler calculations to ensure receiving return signal back to Earth. And then we'll go over a summary and conclusions. Okay, so a number of you might have seen the movie Hidden Figures. It was put together in 2016, and it was dedicated to memorize the efforts of Katherine Johnson, and two other famous technicians, Dr. Dorothy Vaughan and Mary Jackson, who worked on the space program, and they were involved with the trajectories of some of the major space flights, including John Glenn's calculation. And what happened was their computers were just coming into vogue, and John Glenn said, "Look, if Katherine Johnson does the calculations and it confirms what that computer says, I'm going up there." So they had a great emphasis, and I think what happened was, after World War II, there was a great recognition that African Americans were great contributors to the space age and to technology. And that was a great opportunity. This is a little bit of background on Dr. McAfee. He, like Katherine Johnson, grew up in very humble beginnings. He was born in 1914 in Texas. His mother was an educator. His father was a carpenter and minister. He was the second of 9 siblings, very similar to Katherine Johnson. Graduated high school at the age of 15, which was amazing. Got his BS in 1934, and graduated from Ohio State with a master's, and graduated from Cornell with a PhD. And he taught mathematics up until the time he was picked up in 1942 by the U.S. Army on including Project Diana. This is a short video I'd like to show you. This really proves that Dr. McAfee was sort of a hidden figure. And it talks a little bit about the Project Diana. It's in the voice of somebody else, but it's his words.
Can't hear it.
Can you hear it?
There's a button to share audio.
Charlie,
Yes.
we cannot see, we see your presentation, but we cannot hear your voice.
Where do I go, to the front? What do I have to do to get this to work, you know? I'm sorry.
When you go to share video, before you share the video, there's a button at the bottom of the screen that says share computer audio.
Oh, I see it now. Okay, I got it now. I'm sorry about that. I'll redo it. See if you hear it now.
When they came to speak to me initially about Project Diana, they knew that I had done radar coverage diagrams. I had done radar sighting, radar echoing areas, or radar cross-sections, and I had done refraction studies in the atmosphere. I had a paper on this with Harold Webb and Eugene Jerema.
It's very soft.
Colonel John DeWitt was the military head of Evans Laboratory.
Can you hear it?
He had previously tried bouncing radar signals off the moon and failed. E.K. Cebula was the head of the civilian.
You want me to do something else?
No, I think it was.
Charlie,
it's okay.
We hear your video.
What?
We do hear your video, Charlie.
Okay, I'll play it again.
They knew that I had done radar coverage diagrams. I had done radar sighting, radar echoing areas, or radar cross-sections, and I had done refraction studies in the atmosphere. I had a paper on this with Harold Webb and Eugene Jerema. Colonel John DeWitt was the military head of Evans Laboratory. He had previously tried bouncing radar signals off the moon and failed. E.K. Cebula was the head of the civilian branch that we in theoretical studies were under at that time. I computed a radar cross-section of the moon, a radar coverage pattern, and distance to the moon so that they could tell how big the signal would be when it returned. It turns out that they could have detected the returning signal with the previous computations. However, the distance from the moon would have to be greater. Somehow, they seemed to have discounted the mathematical value of this, but they were thrilled when they found out it was close enough. The press release was sent out in January of 1946 and appeared in the New York Times. First radar signal to be bounced off the moon. But I was not mentioned. A paper was written and published that included most of my work, but I was not mentioned. There were a lot of technicians who cried that they weren't named in that paper either, and that they should have been. I was really annoyed when I heard the news reports and found those statements and later read the paper. All of those who were mentioned in the newspaper in that first published paper landed very good jobs after the war. When they came to Fort Monmouth to take pictures, my office wasn't down in the area where the transmitter and antenna were located. Those who knew they were going to come back for pictures went down to get in them and said nothing to anyone. A lot of people say that the work I was very much a part of, bouncing and receiving radar signals off the moon, heralded the U.S.'s ability to launch manned spacecraft. I don't discourage those comments. My whole feeling is that without radar to the moon, they could still have done it if they had been pressing the business of missiles. Like the V-2 that the Germans fire. Just keep building those things and getting better, you could have still done it. But as I say, if people say that this heralded the space age, then I say fine.
Okay, here's just a picture that we just talked about, and Dr. McAfee was part of the theoretical studies group, as you can see. Okay, so as far as the equipment was concerned, as you probably learned, Edwin Armstrong's radar was used, crystal control receiver and transmitter. There was some stability issues regarding the Doppler effect, and we'll talk a little bit about because of the fact that the Earth and the Moon are moving at, and basically there's a difference in the return signal. Okay, here's the major contributions, and one of the major contributions was the coefficient of reflectivity of the moon, meaning what portion of the signal that hits the moon will bounce back towards the Earth. And his team developed that coefficient of reflectivity, very important calculation. I'm still trying to get some more information on exactly the study, but we do have the number. And if anybody has some more information on that, I would certainly appreciate it. But it was a great study because it helped to define what was needed in order to be able to, in terms of the equipment, making sure that the equipment was capable of receiving a signal back to the Earth. The other part was the impact of Doppler effects on frequency. Okay, as we know, the moon and the Earth are revolving, and this caused a requirement for adjusting the frequency of the radio or receiver at the Earth's end because of the drift. Okay, so the coefficient of reflectivity, as we know that on the moon there are a number of mountains and vegetation, and so that if you think about the moon as a disk, okay, or a circle, there's vegetation and there's mountains, and some of that will not reflect the radio wave or the radar wave. So if we first of all think about what the area of that circle would be, it would be pi times d over 2 square, radius squared. And based upon the dimensions, we were talking about 3,664,000 square miles for the circle. The Project Diana, Dr. McAfee calculated that 17.66% of the surface area of that moon would be reflective. So based on that, we would assume 124 square miles. Okay, and we're going to use that coefficient, that sigma there, into our radar equation to determine feasibility of bouncing the signal off the moon. We're going to go through that in the next set of slides. Okay, so think about the Earth as basically a point and a sphere around it. Okay, when we reach the moon, there's a radius from that sphere from the Earth to the moon, and that's the distance, okay, to the moon. The power density would be the power of the transmitter times the gain of the amplifier. That would be the effective power divided by the surface area of a sphere, which is 4 pi r squared, where r is the distance from the transmitter to the target, which would be the moon. Okay, if we multiply that times the sigma we found out in the previous calculation, we would come up with a we would include that. Okay, and thinking about it this way, the signal bouncing from the moon will now come back to the Earth. Okay, so there will be another 4 pi r squared. So the density would be pt g0 sigma over 4 pi r squared, quantity squared, because it's the same distance coming back. Okay, so that's what's called the power density, and that's in terms of watts per square meter. If we realize that the antenna on the Earth is very small, okay, it's got a very small area, we multiply the area of the antenna times the power distribution coming back, that would give us the power to the receiver. Now, the receiver has a certain sensitivity, and that sensitivity is based upon the design of the receiver, which in this case was the receiver we were working with. Okay, and that was about 1.4 times 10 to the minus 18 watts. PT would be the power of the transmitter, 3,000 watts. The area of the antenna on the Earth is only 5.22 times 10 to the minus 7. Very small surface area, right? And the gain of the transmitter would be, in this case, of the antenna for the transmitter is 250 times what the power of the transmitter is. The 250 times 3,000. We substitute all those calculations in and we solve this equation. We basically, what we do is we bring the R4 up here, the PR down here, and if we did the calculation, we would come up with a value of 573,000 miles. That's twice the distance to the moon. So basically, we do have enough power because we would exceed the 1.48 times 10 to the minus 18 watts. So we knew it was feasible. Okay, basically that's what this calculation proved. Okay. Okay, the next part of this was the Doppler effect, and you probably had heard this, I think, in an earlier discussion with I get the first discussion this morning about the radar, is that if you think about a car moving in an observer 1 and 2, observer 1, as the car goes away, the signal frequency gets lower, okay? As you get closer to observer 2, the frequency increases. So there is effect based upon where you sit and how it's related. So what we found out is that the Earth revolves on its axis, the moon rotates on its axis, and based on moonrise and moonset, the maximum variation would have been for the Earth rotation of 795 miles per hour, 185 miles per hour for the moon. So if you add those two together, that's about 198 miles per hour difference, okay? We'll take that calculation now and use it to calculate the actual difference in terms of miles per second. So we have 980 miles per hour times 1 hour per 60 minutes times 1 minute per 60 seconds. That comes out to be 0.273 miles per second. That's the difference. Now, radio waves travel at a speed of 186,000 miles per second. So the difference, if you think about it from a percentage perspective, would be 0.273 divided by 186,000. The radio wave has to travel 2 ways, right? It's got to go to the moon and back. So we multiply that by 2, and we multiply by the frequency of the radar, which was 115 times 10 to the 6, or 150 megahertz, 15 megahertz. That tells us that the frequency drift would be about 336 hertz. Now, the receiver had a bandwidth of 50 hertz. So if you had a center frequency there, you know that because of this 336 shift, if we just kept it where it was at a center frequency without changing that, we wouldn't be able to receive the signal. So we had to be able to shift our frequency by 336. So that was something that had to be known ahead of time to be able to get a successful moon bounce. Okay, so Diana project was a significant event. It was the birth of radio astronomy. Later used to map other planets, a precursor to the US space program. It demonstrated the feasibility of Earth to moon communications. It demonstrated terrestrial radio signals could penetrate the ionosphere for space communications. It opened the possibility for space exploration. And as we know, Diana, the 2 Dianas were named after the Greek and Roman gods for the space program. Okay, I want to play this short video because I think this is a good video that captures the recognition to Dr. McAfee for all his efforts. And that includes not only his effort on Project Diana, but also his efforts at Fort Monmouth and in various areas working in the sensor and reconnaissance area. This was the dedication of the Belmar Post Office, which occurred in 2019. I'll play this short video.
I thank my friend from Montana for yielding.
Gentleman from New Jersey is recognized.
And for he and the ranking member for their support for this important legislation. It is an honor to bring H.R. 3655 to the House today to designate the facility of the U.S. Postal Service located at 1300 Main Street in Belmar, New Jersey, as the Walter S. McAfee Post Office Building. Dr. Walter McAfee was a scientist, educator, and advisor to the U.S. Army Communications Electronics Command and the Fort Monmouth community. Mr. Speaker, I reached out to the leaders of Information Age Learning Center, also known as InfoAge, several months ago and asked them if they could recommend a member of their community whom they believed ought to be honored in this way, and they recommended Dr. McAfee.
I had a problem with the link here. They gave me a problem.
As some of you may know, InfoAge has been the leading organization preserving scientific
We can hear you.
information and communications located at the former Army Camp Evans and a subpost of Fort Monmouth. Dr. McAfee was instrumental in the success of Project Diana, an effort by scientists at Camp Evans to pierce the Earth's outer atmosphere with high-frequency signals, in other words, radar. It was his mathematical calculations that enabled the team to bounce the first radio signals off the moon's surface. Without the success of his calculations that allowed for communication to occur between Earth and space, the achievements of launching the satellites into space or sending a man to the moon would have not been possible. It is the achievement of this extraordinary man that actually helped launch us into the space age. During his time at Fort Monmouth, Dr. McAfee also developed sensors which were used to detect and track enemy movements during the Vietnam War, and served as director of a NATO study on surveillance and target acquisition, high-priority technologies during the Cold War. Dr. McAfee was the first African American to be promoted to GS-16, a super-grade civilian position in the U.S. Army Materiel Command, AMC, and to be inducted into the AMC Hall of Fame. Throughout his lifetime, his achievements were recognized through dozens of awards and honors he received for his contributions to science and to the defense of the United States and our allies. He was known for his love of learning, his high ethical standards, and a great sense of humor. He passed away in 1995 in Belmar, New Jersey. He and his wife Viola were married for close to 54 years and are survived by their daughters Diane, Mercedes McAfee, and Marcia Barra Morris. I'm thankful to my colleagues for their support, anticipated support for this legislation. I yield back the balance of my time.
I think that was a great dedication to Dr. McAfee for all his efforts, and I really applaud that. And again, as we, in summary, Dr. McAfee was truly an amazing pioneer and hidden figure in New Jersey. The support of his parents and his drive were key ingredients for gaining his goals and objectives. His work on Project Diana was paved the way for U.S. space exploration, and his work and life offer young students a great model to emulate and achieve their future goals. And I really appreciate the opportunity to give this briefing. I did this also for Ocean County College. They were very happy to hear this briefing. We're doing a bunch of different briefings on special people, and Dr. McAfee is certainly that special person. Any questions?
Oh, hi, Charlie. You hear
Yeah.
me?
Yeah.
Yeah, very good presentation. Thank you. It was also my pleasure to work in Building 600 at Fort Monmouth, who's named after Dr. McAfee.
Oh, yeah. Well, I mean, in the McAfee Center on the main post was, you know, that's a big brick building. It's still there. I don't know what they're going to do. Eatontown is, you know, changing quite a bit. They're trying to hopefully get the place revitalized, but it's working there 38 years. I've seen a lot of changes to Fort Monmouth.
And it was a great place to work.
Okay, I stopped sharing now, so.
Okay. Charlie.
Hello?
Wow, what math? You know, Robert Johansson, I see you there, Bob. You've seen me at the controls struggling with the math. I always am impressed when I see a formula like that that explains what we do here so easily. And, you know, I just want to say a shout out to Bob Johansson, who is my radio expert. You are the radio expert. And if there's ever anything going on with the Kenwood T2000, which is a fabulous ham radio, you know who's got the answer? It's Bob Johansson. So I just wanted to say thank you to that.
Don't give me too much credit. Thank you, Lori.
Thank you, Bob. Okay.
I
Well,
want to say something to Cindy Stodolo. I read the article about your dad on the on ham radio, and I was very impressed. I got back at the amateur radio. I was a ham radio operator back in the early 60s, and I kind of let it go after a while, and I got back into it. But I was very impressed with all the work that he did in the ham radio area.
Yeah, one of my earliest memories is of his shack, which was fairly bigger than a closet next to where my bedroom was. And so I was very aware, I got very used to that kind of noise. And he eventually had to share it when my second sister was born. And my first sister and I were in the bedroom. There was no more room for the crib, so.
You had to listen to the dits and the dahs, right? You had to listen to the dits and the dahs.
Yeah, exactly. That's why I never mind beeping devices, and other people are saying, what the heck is that? And I'm like, oh.
Well, you know that Thomas Edison, that's what when he was getting engaged to his wife, he used the Morse code to propose to her. So it goes back a ways.
that's great. That's great. Yeah, and anyone out there who has grandkids or young children, you know, my 6-year-old grandson was walking around with a little Baofeng ham radio as early as 6 years old. So get them started early. Give them that Baofeng and teach them about frequency. I think that's really, you know, easily grasped even by a little kid. Any other questions for Charles? Any mathematical questions? He's got Guy, he'll answer your questions. Anybody out there? Okay. So,
I have a comment.
yes, go ahead.
It's interesting that any medical people here, that in ultrasound, redshift and blue shift are reversed.
Ah,
Weird, isn't it?
did not know that.
Yeah, it's kind of weird. Anyway, very confusing when you look at an ultrasound image with Doppler shift blood flow.
What is the frequency? That's my
10 megahertz. It's typical.
okay.
I think there's got to be something wrong there. I'm sorry, Charlie. Acoustic Doppler shift, and it's got to work the same way.
It works the same way, but the image, I have an ultrasound imager.
Well, it's the way they present it, because what's blue and what's red.
Right. But being a scientist, it was very confusing when I saw it at first, because they had reversed it. And I said, is the blood flowing the opposite direction, I think? No, they redefined it differently. It's like, oh, I guess they didn't know about Hubble, etc. Whoever designed the.
They don't know about red and blue sound. That's what it is.
Red and blue.
But when something's heading towards you, you know, it's the if I can say it, and I'm going to hang up here, but the train whistle, right? Train whistle is going to you, goes up, train's going away from you, it goes down, and the same thing occurs with motion for electromagnetic waves. And though I can't prove it, but I suspect it's the same thing for gravitational waves.
We're not there yet, are we, Alan? But we're on our way.
Are slides available for this meeting?
Yes. So now we are going to hear from the McAfee family. Let's see who is here. I'm looking. Are you ready to speak? Where are you? Where are you?
Unmute.
She's
Okay.
muted.
Unmute, yes.
I'm unmuted. Can you hear me now?
I can hear you now.
I was going to say many members of my family are here and I'd like to introduce them if I can quickly
Please go ahead. So
get
let me
into the participants.
let me introduce you, Diane. We were so lucky to finally find Diane McAfee this week. I looked high and low, and because I've changed cell phones so many times since the last time that we met, I could not find her contact information. So I did reach out to our congressman, Chris Smith, and because he was instrumental in getting the post office named after Walter McAfee. And lo and behold, Chris Smith had her contact information, and just this week, Diane got in touch with me, and I welcomed her to please speak about her father's contribution. And so, thank you, Diane, for joining us. The floor is yours.
You're welcome. I want to thank Charles Cebula for that excellent presentation. Some of what I say may be a repeat, but first let me tell you who's here. Wanda McAfee, his niece. I'm just looking at this list and I don't want to miss anybody. Patricia McAfee Owens. Okay, keep going. Marsha Barra McAfee Morris. I'm sorry, Marsha McAfee Barra Morris. This is my own sister. That's why I struggle with her name so much, I guess. And LaRue McAfee Smith, LaRue McAfee. And that's his niece and great niece. And let's see. Sorry, the Zoomer is doing very funny things.
Diane,
Travis and Caroline.
I invite Fred Carl to go ahead and say something about Dr. McAfee. Fred, go ahead.
Oh, thanks. I've done a lot of oral history interviews from people associated with Camp Evans, and I had a list of like, did you work with Dr. Zoll? Did you work with this one, that one? Did you work with Dr. McAfee? And to a person, a fond glow of remembrance would radiate from people. The first time I thought, wow, they must have had a good relationship. When it got to be about the fourth or fifth time, I was in awe. I can't imagine what a great person it was, or Dr. McAfee was, and how well he treated people. Somewhere along the way, I read he had described his working relationship with his coworkers, and he said, I try to treat everyone like an individual or as an individual. What an excellent comment for what's going on in the news today. And so he was ahead of his time in many ways. And thank you for letting me share that.
Thank you, Fred. Go
Thank
ahead,
you for
Diane,
that.
yours.
Okay, well, I don't want to make this go on too long, but I've got to say that his sister is here, the last living sibling from that generation in our family, because I see her name, Dr. Velma McAfee Williams. And I don't know if she wants to say hi. Aunt Velma, do you want to say hi? Can she say that? Can she? She can during the
unmute
questions.
You can unmute temporarily by pressing the space bar.
Okay.
I can do that, or you can do that?
You can do that.
I can do that. Push the space bar. Okay. And I also want to be recording. Can I do that?
You can record yourself, and this entire meeting is being recorded.
Okay. I don't see a record. Oh, I see a record button here. I have to give permission from you, it says.
No, you can record yourself. The entire program is being recorded, so I can give you a copy of that.
Okay, I'll go ahead and fix that out later. On Friday, August 30th, 2019, under an act of Congress, the post office in Belmar, New Jersey, as you've been told, the community where my father lived, worked, and raised his family, was renamed in his honor. Previously, on October 27th, 2015, my father was inducted into the Army Materiel Command, AMC, Hall of Fame. He also had a building complex named for him at Fort Monmouth, New Jersey. and after the closure of the fort at Aberdeen Proving Ground in Maryland. What was remarkable about my father, even more than his brilliance, was his perseverance and resilience, what he went through in order to acquire the education that enabled him to make the contributions he made to Project Diana, as well as several other Army projects, research projects, was nothing short of remarkable. In the words of my sister, these are remarks from the dedication, the renaming of the post office that my sister gave, Marcia Barrow Morris, who based her comments on words from a speech in which my father had described his educational path. Quote, his most trying time was at Ohio State University, where he earned his master's degree in physics. Black people were not allowed to be teaching assistants at Ohio State at the time, nor could they stay in the dormitories on campus. At times, my father was working 3 or 4 jobs simultaneously to cover the cost of tuition, housing, and educational expenses. His department chairman actively discouraged pursuit of the PhD, and according to my father, hollered at him for not taking an industrial arts course. He was, after all, only going to be able to go back south to teach in a Black school. However, I once heard my father say that having seen the effect of a dream denied on his father, who wanted to be a pastor, a minister, he had decided that he would never give up on a dream, his dream, without making every possible effort to achieve it. And of course, he had supporters. He got his BA from Wiley College, a traditionally Black college in Marshall, Texas. And there he had professors that he kept up with who knew he was brilliant and wanted him to succeed and that sort of thing. So he had support from his family, and I'll talk about that in a minute. It goes without saying that my father and mother had a profound effect on me and my sister, especially in shaping our approach to education. First, they instilled in us a belief in the value, the importance of education. They were both readers, and they encouraged us, not to say pressured us, to excel in our studies. And this is something his colleagues may not have known about him. Not only did he love physics and math, but he was an omnivore, a true Renaissance man. He loved literature, especially poetry. His favorite poem was a sonnet by County Cullen, an American poet of the Harlem Renaissance, which begins, I doubt not, God is good, well-meaning kind, and ends, yet do I marvel at this curious thing, to make a poet Black and bid him sing. I cannot, I'm backtracking a little here, I cannot discuss my father's love of education without noting that it was developed first of all in the bosom of his family. His first teacher was his mother, my grandmother, Susie Johnson McAfee, who, although she was never able to use the certificate she had earned to teach in public school, did teach her 9 children, all of whom earned degrees in math or math-related fields. And then continuing with his influence on our family. Not only was my father a profound influence on the education of my sister and me, he had a significant influence on the development of his nieces and nephews, to a degree which I did not appreciate fully until I reread the comments of my cousin, Professor Leo Cecil McAfee. He's emeritus from the faculty at University of Michigan now in the Department of Engineering, and preserved in the congressional record that was sampled in the video that Mr. Cebula, Charlie Cebula, just showed. Okay, this is what my cousin Leo said. Vividly, I remember a day at my elementary school. I was a 5th, 6th grade student at the time. My father, the school principal, proudly showed us a newspaper article reporting that Uncle Walter was a recipient of a Secretary of the Army Presidential Fellowship. This event is vivid in my memory because I decided that I wanted to earn a PhD and be a scientist, even though I did not know what the career of a scientist involved, or the career of an engineer, or for that matter, any other career other than educator, teacher. That event and that day have remained etched and stored in the forefront of my memory for perhaps 63 years now. Cousin Leo goes on to share that Walter McAfee, his Uncle Walter, had a profound influence on 3 and even 4 generations of nieces and nephews. And that some of how he influenced his family or his influence in his family. Thank you for this opportunity to share my personal reflections. I'm going to stop here and see if anybody has any questions. That's all I have to say.
Thank you, Diane, for that account. So many questions. Please, if you have a question for Diane, unmute yourself and go ahead.
Hello, Mercedes.
Oh, hi, Leo. How are you?
I can help you identify your family here. I got the participants pulled up.
Oh, thank you so much, David.
So
go ahead.
There's you, and you on the first on the list. There's Benita Copeland, Cecilia's daughter. Benjamin Taylor, Cecilia's son. Cecilia and Benjamin, son. I just put them both in there. And Cecilia and Benjamin Taylor, of course. I hope I don't miss anybody as I go through here. Dr. Velma Williams, McAfee Williams. I see Vicki Smith.
Can I stick in a couple of names?
Please do.
This is my sister, Marcia, and my brother-in-law, Lorenzo Morris.
Melba Robinson, Leisha, I think.
Yeah.
Linton, Travis, and Carolyn.
All cousins of us, my sister's generation.
LaRue McAfee Smith. And then my daughter, LaRue McAfee, Leisha Linton. Leisha's on there twice, I guess. Okay.
Wanda Joyce.
There we go.
He's already been identified.
Okay.
Hi.
It's an honor to have you all.
I am so happy to have the McAfee family represented here, as you should be. And let me just say at this point, as we are getting ready to share this with Frank O'Brien, who will be the next speaker, think about what it was like 75 years ago in terms of the future. What will this be like in 75 years from now, when the 150th anniversary of the moon bounce is celebrated? Who will do the celebrating? I don't think I'll be around. I wonder if any of you will be around. I don't know. There was an article in Newsweek a few years back about the first person that will live to be 150 years old, having already been born. It is possible. We've got the technology to extend life. I don't know if indefinitely yet, but who will carry this on, if not the future? Part of what we do here at InfoAge is exactly that, is try to keep history and science alive for the future generations. And so I'm going to do a little infomercial again. Please, please, please donate. You see how important this is, how much information can be lost. The SCR was thrown over the side of the hill here at the Diana site. Let's not let that happen to the future. Let's preserve what we have. This place is the place where the beginning of space exploration happened. So please donate. Go to isec.space, where you have the opportunity to donate. Go to our infoage.org website, where you have the ability to donate. Please, please, anything helps and keeps us going. And Walter McAfee is absolutely essential. I'm glad I've had some individual direct messages saying, thanks for setting the record straight. This is the time to do that, to set the record straight about all of the people. A few years ago, I had a woman come in, and she was 95, I think, She was in a nursing home, but she was brought here by a nurse, and she was one of the secretaries, a secretary for the Project Diana. And I said to her, my gosh, without your letter writing, without your keeping record and track of everything, this wouldn't have happened. Everyone was essential who was involved in this. Let's keep it going. Let's keep it alive. Walter McAfee was an essential member of this team, even if we only have the 5 names that we are used to hearing. But I'm very glad to add Dr. McAfee to that group of people. So we're a little early. Is Frank O'Brien here? Frank?
This is Marcia.
Yes, Marcia, go ahead.
I just wanted to add one more name from the other side of my family, Norma.
Hey.
Norma Gail Morris,
Oh.
sister-in-law.
Shout out to Norma Gail Morris. Hi. Glad you're here. I am now. So, Frank O'Brien, are you here?
I certainly am.
Okay. So, Frank, thank you for sending the information that you sent me. And I imagine that you want to go ahead and start thinking about your conversation. We're about 20 minutes early. I have other things that I can do until 3 o'clock, or would you like to start now? What do you think?
Well, I don't have any problem with starting right now. My only counter to that is that we scheduled for 3. I don't know if there's a number of people that would be jumping on at 3 expecting things to start. I'm guessing no. And
Lori?
it's probably been a little bit of a long day for everyone.
It has.
Lori?
Jill,
I'm sorry my camera doesn't work, but I have a little humorous aside, something my mother worked, this is just to show, you know, the human side of these larger than life heroes. My mother was a high school student during the war in Asbury Park, and because the men were all off to war, they recruited a lot of the girls to work in. So she was recruited to become a draftsman. She worked out at Sandy Hook, and when she was new, as a hazing prank to this young, naive little girl, they sent her down to the radio lab, which of course had vacuum tubes and all kinds of tubes. And they asked her to go pick up a few for them and bring them back. And she wrote down what she was sent down there for, and she ran down there and she read it to the guys. And she said she needed to pick up 2 fallopian tubes. Of course, she never lived it down, but I love that story.
That must have been a hard thing to do.
I know.
May I add a
Well,
little?
she could have said that I have it right here, but
Well, I think she was so naive, and back then I'm not even sure if she knew it at the time what it was. But
that was
I
the
just always
right
love that story. It makes it much more personal and human, and that's the type of stuff, you know, that happens in offices. So
Yeah, and I think that is the purpose of this at 75 years from that date, and how many changes we have seen, how many changes we're seeing today. Things that are happening today will, shape our future in this country, and the kinds of access that the everyday average person has to education, and not only to education, but to work, do good work on teams that they may not have been admitted into in the future. And I've received several direct messages saying, I'm so happy to see women here. Yeah, women in the future, people of all nations, being able to contribute. Our minds are sharp, men, and we can do good work right alongside everyone else. So I am very happy to see so many women here, and I hope that we can keep that going. We can encourage young girls to seek careers in science. We can tell them to be mathematicians. We can tell them that they can be an engineer, and that they can fully feel comfortable in the workplace without fear of any kind of harassment or any impediment that they might have for the contribution that they can make in science. And I think that we are arriving at that day. So ladies, keep it going. And I'm glad that you're here. Go ahead, Fred Carl.
Lori, to tie in the missing radars and things like that from the museum and the fallopian tube story, I'd like to add the next chapter. So that was a common hazing thing to the young and naive. So they sent a young man down there, and when he got to the desk, they said, "We're out of tubes, fallopian tubes. Come back in a week." So the guy did. And when he got back and said, "They're out of fallopian tubes, come back in a week," the guys were like, "Whoa, how's this going to play out?" You know, so I said, "Okay, we'll send you back in a week." So the guys in the tube shop, they put together a little box, put cotton in it. They did their best job of blowing glass to look like fallopian tubes. And when the fellow returned, he came back with a set of fallopian tubes, right? In their custom box and all that. And I was told that was put in the Fort Monmouth Museum.
Oh, no.
So they labeled fallopian tubes.
I guess, I think it's on top of Al's SCR 270 radar.
I love it. Thank you, Fred. That's a riot.
It's great. It's great. We recently had a donation of a very sophisticated looking antique tube tester. And I wonder if they would have worked on the with the tube tester that we have today. Okay, let's see. Anyone else?
Yeah, I just wanted to say that that was a rite of passage at working at a TV repair shop for a young person, like as a gopher, go to the parts counter and get a fallopian tube. And any women that were like standing around, they'd be chuckling, and the young man would wonder what it was. That was so funny, you know, because he didn't know.
Wow.
So I just thought I'd contribute.
I have to
Thank
add this.
Can I say something, please?
Well, I was going to add this. My experience at RCA Princeton Labs was similar but different. They didn't go with the fallopian tubes, and I don't know that they necessarily were intending it as hazing, but I had designed a circuit and then I was supposed to solder it together and get the parts. So they said, all right, well, figure out, what your components are that you need. So, I knew Ohm's law and I came up with all these resistor values and everything, not knowing, because I had never spec'd out parts. I didn't know they were sold in certain unit values. So I came down with all these different numbers on my sheet of paper and handed them to the parts department, and they are all laughing hysterically. They were like, no, let me explain. So it wasn't really a hazing, but it is a story I will never forget. I mean, I had the numbers right, but they're just round up. It's okay.
These are great stories, and they make up our future, right? I can imagine, Rebecca, that it made you a little bit more stalwart, and you were like, hey.
Hey, now I'm one of the guys. Oh, I did want to ask, since I just have a minute here, I just wanted to ask to the family if any of you have his slide rule. I have my father's slide rule, and that was a big deal because, there were different, really good ones were more finely, adjustable and stuff. Do any of you remember, packing it, or did you keep it? Or I hope somebody in your family has it, because that's how they did those calculations 75 years ago. There were not any calculators.
You'll have to ask my sister. She was the mathematician.
Where is she? Maybe she has it. Maybe she has it. That was a big deal, having the slide.
No. Or if I have it, I don't know that I have it. I did notice in one of the presentations earlier today that the guy was working with a slide rule, but I have no idea where it is.
Oh, wow. Wow. Well, it might have belonged to the Army. You may have had to give it back, but I have my father's. He was a
teacher, and he would not let me or my brother touch it. This was a big deal to him. He had gotten it for college, and he's like, this is a very good slide rule. You can use the cheaper ones, but not this one. So yeah, that was a big deal. I hope you folks can track it down if you can.
Laurie, can I say something?
Yes.
Yes, okay. It's my name's Ben. I'm in the UK. It's getting a bit late here, so I'm going to pull the plug. But I'd just like to thank you and everybody for the presentations.
Thank you for joining us from the UK.
Thank you. Good night.
Good night,
Good
and
night.
have a wonderful evening.
I have a quick question.
Yes.
Are you going to put any of this, are you recording this? You're going to put this up on the website in any way?
I plan to put this up. This is being recorded, and I plan to put this up on our website. Yes, absolutely.
That'd be good, because I'd like to share some of it with some people.
Yep. So you should look at isec.space and you'll see this. I want to show a video that is available on YouTube. It's very short. It's 1.5 minutes, but I think it's appropriate. And here we go. Hopefully I will get this up and running, and let's take a look. Give it a second.
The vivid imaginations of H.G. Wells and Buck Rogers never cooked up a more fantastic experience than the Army engineers at their laboratory in Belmar, New Jersey. Banks of instrument panels control a radar installation that gives man his first actual contact with the moon. An amazing round trip of over 477,000 miles. Ready to shoot the moon. The radar antenna is pointed directly at Luna, and the thrill of a lifetime is in the making. Three 2.5-second trips up and back. If you're ready for another trip to the moon, let's go. That was a 180-cycle note, just about like your home radio. It opens up unlimited possibilities for interstellar experiments, according to Colonel DeWitt, who supervised the project.
Calculations showed that radar equipment could be put together which would reach the moon and return. If one allows the imagination free rein, many future possibilities appear. Spaceships carrying passengers at thousands of miles per hour can be controlled and communication established with their passengers. For we now know that the Earth's atmosphere can be penetrated.
And I just thought that was very interesting to show. It's one of those things that when I first started here, I found, and I thought, wow, imagine the courage to be in a newsreel at a time when it seemed impossible to say something like that. And maybe we'll have spacemen in spaceships. You know, it's like me saying, okay, and we are going to inhabit Mars and all will be well. It took courage. It took courage for these men to do the work they did and be willing to be discredited, and they weren't. And that's the kind of courage that we need as we look to the future in space exploration. Soon, we will invite Frank O'Brien to begin speaking. Frank,
Yes,
are you there?
excuse me.
Yes, go ahead.
Yeah, just quickly. Does anybody know if there's any clean Diana video floating around?
Right. Oh, the resounding not echo.
Well, just as a thought, because it's amazing what you can find, the National Archives has copies of films going back since the creation. So, and they probably actually have a film of the creation. I forget the website. You can easily find it. They have video clips. Well, of course, National Archives, they have something of everything. And that would not be the worst place to start. Most of the videos that you'll see on YouTube and all the rest, like what Lori was just putting up, have been copied and copied and copied and compressed and lost. So honestly, something like that, going to the archives would not be the worst place. Since it was a government operation and all the rest, it may take some digging, but it's not a crazy idea to start going there first.
Frank?
And they're usually early generation copies.
I will dig in my records because I did go to the National Archives. I brought a projector. I displayed the films on a wall while I was recording them with the VHS tape.
Oh, God.
I know. Well, this was before you could get them on the internet, but they might be better quality.
You didn't use your phone?
The phone I had then had a dial wheel.
Mine had push buttons.
I think this is the video that appeared in one of Neil deGrasse Tyson's revival of Cosmos. And I sort of remember it looking a little better. So I wonder if they did some enhancing.
Of course. Yeah. I don't have the ability to do that kind of thing, to take that video, but I have watched that.
No, but I think I'm just wondering if that might, fill.
That might be a resource.
Yeah.
That's right, Frank, exactly what you said. You probably had access to the original video and was able to change it. This is a very strange little aside note. And, we actually have someone on staff here as a docent who was the head of MUFON, which is an organization that takes accounts of people who have seen or experienced a UFO, and they record it so that they can have some sort of list of what people have said they have seen. There's no substantiation for this, but it is just an organization that does that. But what I have learned in speaking with people who do radio astronomy, in particular FAST, this massive $18 billion project in China, they are looking for signals. We are actively looking for K2 planets. We want to know whether we are alone in the universe. We want to know if there is anything else out there that is able to produce a radio signal that we might be able to hear. And we know now, because of the moon bounce, that we can receive a radio signal from above the ionosphere. And recently in the news, there has been information about a signal that is coming from Alpha Centauri. And there is a consensus among a few people that it does not seem to be natural. Usually when a radio signal is heard, it can be identified as something that is probably natural, such as the pulse of a pulsar, for example, because a hydrogen does emit a radio wave. But this has been difficult to classify, and you never know what we're actually going to find out there. Dan, are you willing to say anything about that? Debunk us.
It was the microwave oven, I believe. It happened at lunchtime, wasn't it?
It's a microwave.
Yeah, I think InfoAge is a science organization. We should not get too far off the real axis here.
Yeah.
Thank you, Dan, for that. I love it that you bring us back down to earth. That's wonderful. But you're absolutely right. There's just so much. There really is so much to consider and so much to do.
I just want to interject.
Yes.
There are serious efforts at looking at possible signals. I'm not saying I believe in this, but there are radio astronomy anomalies. You expect things to act in a particular way in terms of their changes. And I remember in recent literature of some of the work that is going on looking for new galaxies and things like that. And I can go and look up the reference where they were talking about some anomalous characteristics. And this was serious radio astronomy. It wasn't some people talking about a visit or disappear from the earth. So there are serious efforts, and there are things that occur that, it's really not the little green men, but have scientific basis to them.
Thanks, Alan. So I love the fact that we have two good views. Dr. Dan Marlow says, this is purely science, stop fooling around. And Alan, Dr. Katz also says,
I want to echo that the scientific end. This is Joan speaking, Joan Moffinson. Can you hear me?
Yes.
Yes.
My dad talking about somebody, his last name was Hynek, Hynek. He was fascinated by UFOs. My father was fascinated. And I remember this because I went to college with a young woman named Hynek, and my father said, oh, he's the one who, and he was quite respectful of his research. So I guess I'm on the scientific side of this debate.
Yeah.
Oh, I remember years ago, I think his first name is Alan. Oh God, when I was a kid or something, I remember picking up one of his books, and this guy is nuts. He sees little green men everywhere.
No, this was.
well, let me just say that I don't look for little green men. I'm not interested in little green men, but I am interested in radio. And I think that that's, for me, the serious side of it. I am interested in radio. I am interested in listening. And that, I think, is science.
Yeah. Yes. Lori, if I could comment, I don't think there's actually a lot of daylight between me and Al on this. I think, one just has to be very careful about how we go about this. I mean, SETI, for example, was, people thought it was speculative, but it was a respectable program.
Yes.
But, it's easy to get carried away.
Yeah, you could easily go on this.
Dan, the reference I'm talking about has nothing to do with UFOs. It has to, in pulsar theorem, pulsars get large and they get small, and how fast that occurs and things like that when you deal with the spatial angle involved. I got to go back and look at it, but it was speculation that from the physics that this type of change was very unlikely in terms of the observations.
So Jocelyn Bell was, when she first saw her signal, it looked like it might be, from unnatural causes, let's say. And she reports being greatly relieved when, it was figured out that it wasn't. There was a natural explanation for it. She would be able to finish her thesis more quickly.
Well, thanks, Dan, for that. I do recall that Stephen Hawking, before he left, although he was, basically a popular celebrity scientist, he did say that if we did find other life like us, biological life, that it might not be such a good idea because we don't have what it would take to find them. So if they can find us, they have a lot more than what we have. And that would not be so much in our interest. So let's leave.
Yeah, the hour has